Yeah, welcome to our first, Magic workshop. Magic is GenAI Media Generation Challenge workshop. So there's been a lot of generative video works over the years. Right now I'm putting down just looking back at 10 years of generative video work. 10 years ago, Ian Goodfellow published GAN, generative adversarial networks, which showed potentials in using GANs to actually generate media. Since then, GANs have been sort of like the mainstream method on producing nice generative results. We have GANs, DC GANs, the big GANs. Most of the work also spun out to form different applications. We had Prisma Lab showing up as style transfer tools. That's been on mobile devices. Adobe Photoshop also adapted style transfer methods into their work. More recently, VQVAE showed that you could generate more high resolution results. And then more recently, also like DF GANs, and then I think the latest work is from Giga GANs. Separate from GANs, we also have the other lines of work also using recurrent or regressive networks to produce synthesized images with the draw work by Gregor et al. And later by Pixel, CNN. Most of these works were not capable of generating that great of results compared to, I think, GANs. So GANs have been still the mainstream work. In 2022, there's work on using denoising, showing that denoising can help actually produce high resolution images. The DTPM work by Ho et al. And this sort of brought forth, I think, a different paradigm of using generating generative media. In 2022, we have the latent diffusion models from Rombach, and that has sort of spun out a lot of new works with stable diffusion showing that you can actually generate very good results. On the startup side, we have also the Midjourney, which has been always the popular app that the industry have been using. Well, as mentioned, industry is including both the tech industry and also the art and game industry. This has been revolutionizing how people would actually generate art and use these to actually inspire how they actually produce new designs. Now, compared to like probably 5 or even 10 years ago, there's an explosion of different generative works. With the auto-regressive approach, so you also have the Imagine, Party and Muse type of approaches. DALL-E 2 is also regressive type. With DALL-E 3, actually, I don't think for DALL-E 3 it's also a diffusion-based approach, but now there's also like using flow matching methods to actually improve on image generation, such as used in stable diffusion. Along these with generative works, we look at the benchmarks. Most of them has been recycling some of the image recognition works. And earlier, when in the GAN work, they all used MNIST or CIFAR images. This typically generated just 64 by 64 images, fairly small. And then in 2016, we started using much larger images, such as using the CUV dataset and MS-COCO, looking at how we can actually generate images. And then fast forward to 2021, there's more works on T2I, and now new benchmarks on doing T2I benchmarking. So from DrawBench, Imagine, they have the 200 prompts to measure performance. Party prompts, which is a larger data set of 1.5K. TIFA, I think, 1,000. And then T2I comp bench, which looks at particularly spatial relationships and If we create a data set of almost 6,000. And then also DALI, the design bench, which is based on that, I think ChatGPT 3V to help with breaking down results into various design aspects. From these, there's also more specialized benchmarks, such as the text benchmarks from Good Control, diffusion, text diffusion from text diffusion, text benchmarking, which is the Mario Eval. And then, of course, there's image edit, including some things like the image edit benchmark. From these, we'll see that there's a lot of different benchmarks. Limitations are that since every work is actually published on its own, it's really hard to say that there's actually universal and comprehensive benchmark. Like T2I CompBench or the text base, it's specialized towards actually what they're developing. So that opened up an opportunity where we see like we should probably try to put forth a workshop or challenge or a framework so that we can, as a community, agree on what we can use to benchmark these type of approaches. So in that sense, we want to have both a benchmark that is both universal accepted and comprehensive. The other challenging thing to these benchmarking is that if evaluations of generated images is still with automatic metrics is not reliable. I think in the old days, probably with GANs, when we are not able to actually generate good images, those are good enough. However, with the growth of this past few years, we see that there's more and more much more better results. So it requires human evaluation to look at the fine creatives and determine what is right and what is wrong. Finally, not all human evaluation frameworks can be universal. This comes also from the fact that images are generated better and better. So it's really hard to determine what is right and what is wrong. And it requires sometimes human experts to look at it. The plain and simple way of just looking at images and seeing that they actually align to the prompts is not necessarily that easy anymore, because sometimes if it's just one example is like given flags, if it's there are flags that are similar colors. So if one is the other, it'll be harder to determine which is what. So we also needed a framework where we can actually go into the details to look at how we can evaluate these much more easily. So with these in mind, we try to organize this workshop to try to push forth effort on trying to be able to run this run a challenge every year, so that we can the community as a whole to agree on how we can actually do benchmarking. So I think in this workshop first, we will propose to do two major challenges. One is the text-to-image challenge, text-to-image generation challenge. In this track, I think what we give participants is descriptive text inputs, and then we would ask participants to send images to us, and then we would help with benchmarking the results. This initial data set would be 4,000, details of which we'll leave for later for our Tianhe to talk about later. The second track is the text-guided image editing. In this case, we'll give participants text, instructions, and images. These two pairs form, I think, the data set, and participants will basically use these two to generate results and then submit the images to us for evaluation. So that's what we have for the challenge. Okay, so the rest of the workshop is organized as follows. There's going to be two sessions. The first session we have Professor Junyuan Zhu to present his work on known issues with FID and FPD. Followed by that, we'll have Sergey from Snap to talk about video generation, past, present, and a new hope. And finally, we'll have Richard Zhang from Adobe to wrap up with the sensitizing opt-in and enabling opt-out for text-to-image models. From there, we'll take a 20-minute break. And then we'll follow up with the second session from Yuan Zhen from Google, giving a talk on controllable media generation. And Tim Salomons, also from Google, presenting his work on multi-step dissolution of diffusion models via moment matching. And then from 4:20 p.m., Tianhe will announce the competition results, and then we'll have 4 quick presentations from participants to describe their work, and then we'll give out the awards then. And then finally at 5, we'll have a panel discussion on progression of generative AI media now and the future. We have Junyuan, Richard, and Ishan Misra as our panelists. And then we'll have Kevin, which we'll introduce later, as our moderator. And we'll close at 5:30. With that, I'll pass it on to, I think, our first keynote speaker, Junyuan. Thank you. Are you able to join from? Okay, great. And let's stop sharing, and then you can stop. Sure. All right. So, just use this.
I don't project to the.
You just
okay, yeah.
project and down again.
Okay, good. Yeah.
So Zoom, use a share. Okay,
sure. Yeah. Open the video. Or share it? Great. I lost my notes by anyway. So I will talk about some known issues with FID and FED. Volume. Yeah, do you hear me better? Great. So I talk about some known issues with FID and FED. Just to as a quick disclaimer, it's the issues known to me, not necessarily it's all issues we will people know in the community. Okay, so maybe a subset of all the issues with FID. So we talk about hopefully everyone has no FID, but it's basically you have a bunch of real images, you generate a bunch of images, and then you try to compute some distance to get some number in your table, and then you pass these images to inception network, and you extract some features, compute its mean and covariance matrix, and then you compute the pressure distance. Has a closed form solution. That's why people are using it. It has a bunch of other steps which people sometimes ignore. So, for example, you do need to resize the images to 3 by 300. Maybe you're generating 12 by 12 with them to resize images. Your original data set might be even bigger, so another resizing step here before you even train the model. Okay, and you might need to quantify it. Sometimes you store the images into PNG, JPEG, some NumPy files. So there are some steps in between. So somehow the FID is being widely used. Even it's actually popularity lasts maybe longer even than the game model itself. But anyway, it's still being used, whether they like it or not. And people have always benchmarked their models using FID in addition to other metrics like clip, for example. It's still being used in text image generation. Okay. Now, before I mention some issues with FID, I do want to give some credits to FID as well. So I try to mention why what's popular. So this is my educated guess. First of all, is all the metrics have issues, right? So but this FID is better than a bunch of other metrics for inception score. People are aware of the issues of inception score. So it's kind of worse of it's better of the worst candidates, right? So it's kind of better than the other metrics. And second, I mean, it's very model agnostic, so you can apply the FID to GAN model, but also regressive model, diffusion model, flow-based model. It doesn't require the model to produce like a log likelihood. It does not require model to have a low-dimensional latent code. So it's very universal. That's why everyone's using it, right? And arguably, it's relatively cheap and fast to compute. For example, if you apply a different metrics for this classification accuracy score, you have to retrain your image classifier on the generic images, which takes a day to evaluate your results. So you do want something which are cheaper and fast to compute, so you can check the metrics of every epoch or every 100,000 iterations. So you do want this properties. Arguably, kind of covers some diversity and realism. So if you generate only one good results, the FID can kind of capture it a little bit. So it's better. People prefer one metrics than over like 10 metrics, and so you only outperform the other method in 5 metrics. So people like to outperform other methods in 1 metrics. Okay, and then it's arguably easy to reproduce. Part of the reason is there are some standard libraries. The other part of the reason is everyone is using it, so it's a chicken and egg problem. It's easier to reproduce numbers of other methods compared to something like user studies. So yeah, FID might have a reason to be popular. But I have some, I feel there are some issues with FID. Lots of issues has mentioned by other researchers and groups. I just repeat here. The first issue here is we assume FID assume the images follow the Gaussian distribution, single Gaussian distribution in the feature space. But even you look at the standard like diffusion model, like you try to map one Gaussian to 2 Gaussians, so the FID doesn't seem to apply here. Like how do you even compute it's a 2 Gaussian, right? Or why do you compute it, assume it's a 1 Gaussian? Maybe this single Gaussian assumption might hold for some single category data set like faces, which are aligned faces, always the same subject. But it's very hard to believe that all the images that we're generating with all kind of random crazy text prompt and you average them is a single Gaussian. So it's very hard for anyone to believe. So I do think this Gaussian assumption is kind of need to pay deserve some attention. And second, let's say yeah. So anyway, everything is Gaussian, right? Even diffusion model assumes it has some Gaussian distribution. So that's what we can do. But the other issue here, the practical issue is it requires lots of images to compute FID reliably well. For example, here is the FID, the same model, actually these are test images with respect to the number of images. So if you sample more images, your FID is decreasing. So it doesn't make any sense to compare 2 models if they're using different number of images. So I thought you need to be careful about that. And let's say the FID always compute like 2000 by 2000 covariance matrix. So at least you kind of need 2000 samples to get a reasonable estimate of covariance matrix, right? So preferably people using like 50,000 if you have that data. So there's a very nice paper called kernel inception distance called KID, which basically try to address a bunch of issues. So if you have a small data set, you do want to use KID than FID. Okay. And some other issues people haven't paid attention to, which we recently discovered, is so there are a bunch of things happening before you compute FID. There are some resizing business. There are some quantization business, whether you store image in JPEG or PNG or whatever, or you don't convert it to 8-bit. And one issue which is downsampling and resizing issue is sometimes different deep learning library resizing images differently with different flags. So it's a very subtle issue, but it's an issue. For example, if you just downsample image by 2 times, by 4 times without and then by 8 times, you get some kind of aliasing artifacts, right? So you get some aliasing artifacts here. So most people will do is they will apply a filtering before you downsample the images, okay? And but somehow in some libraries, they implement the filtering with the fixed width. So you use the same kernel, even you downsample 2 times or 3 times or 8 times. And this will cause some issues. This should not be fixed. These filters should be adapted to the downsampling ratios. So if you fix it, you still get these aliasing artifacts, although better than not filtering it. But if you actually also adapt the kernel size, you will get something will look much nicer. Okay. Look like this. So again, there's a comparison. This is with fixed filtering, get some aliasing artifacts better than near stable without aliasing. Okay. And it turns out most of the library they with the default flags they do use fixed filters downsampling size. The thing which actually works is PIO is by default is adaptive filter size, and most of the FID library was actually using fixed filter size when downsampling images. Now you may ask, oh, why does that matter? Why do I care about this downsampling an image? So the reason why it matters is sometimes you downsample image. This is with adaptive filter. And if you use a fixed size, you will get aliasing artifacts for images as well. And again, do a comparison. Here, this is okay. This is fixed with pre-filtering. So this is adaptive ones. You can see some artifacts here. Okay. And now the thing why it matters is it will change the inception features. So if you do apply different downsampling filters, you will get different inception features, and they look quite differently. It's not just slightly different. They're quite different. And if you apply different filtering when you compute the FID, you will get different results. Okay. And it's also reflecting the changes of FID. For example, if you don't do any filtering, you get 2.68. And you apply some smoothing, you get a higher FID, which is kind of funny. But if you do the correct filtering, you get even a higher FID. So oftentimes what happens sometimes is people will just try a bunch of flags and try to get the lowest FID, which we are not supposed to do, but happen sometimes. Or maybe different papers in different filtering. Right? And the same applies to this compression business. For example, this is JPEG compression. It's very hard to see the difference, right? Even 75, it's hard. But the issue is if you feed an image with different compression ratio, you might get different inception features. So inception network is very sensitive to the compression ratio as well. This is 75. And you go to 90, and you get something different, which it will change your FID number as well. And this is the PNG without any JPEG stuff going on. Okay. But what makes things quite funny is that JPEG 90, JPEG 75, they all look slightly different. And if you compute FID, you will get like a quite different FID. If you compare the JPEG 90 FID with PNG FID, it's like 6. It's pretty high, right? But they should say, but if you look at the images, they are perceptually very similar. And so what makes things more funnier is basically lots of computer vision data set is using JPEG 75 for the real images. And if you train a model on JPEG 75 images, and you use PNG as your generate images, when you generate images such as a PNG, you get 4.0 FID, which is fine. But the issue is if you actually compress your image slightly with JPEG 87, you get even a lower FID. That's like 3.05 lower. So what happened is basically the network try to mimic the 75 compression, JPEG compression. It kind of does a kind of half-baked job, so you get 87. So that's what happens. So we can know like the FID was actually sensitive to so many different things. So we actually released a library which has been downloaded by 20 million times, which I don't know who has so many GPUs, but anyway, so it's been downloaded by lots of people, and we try to implement every resizing and quantization more carefully, which release called Clean FID. So the recommendation is you do want to pre-filter the images adaptively when resizing. When you prepare for a training set, you don't want to apply very aggressive JPEG compression for a training set. Okay. And so there's also a choice of feature extractor because we need to use the inception network. to extract the features. And there was a very nice work by the media team and Yakov's group, which says the inception feature, the computer FID, and they do some kind of heat map visualization using GradCam, and they found out that actually the FID cares mostly about the background, even you are trying to generating a face. So what happened is basically the inception network try to classify image. For example, you classify image as a microphone, and the FID actually care about the microphone rather than the faces. So this is a very nice work from media Yakov's group. And the same apply here. You might got like a seat belt, and you might think this is a seat belt. So somehow, and they question the role of these like semantic categories when we compute kind of perceptual feature like FID. And what they found is they found that FID does not reflect the image quality. For example, here is model which they think is a worse model. Everything is kind of worse than the original StyleGAN 2. But this model actually achieve a slightly lower FID than the StyleGAN V2's FID, right? But one thing they recommend is maybe we should replace the inception network, which focuses on semantic categories, by a clip model, which might be more self-supervised learned. So actually, they found out if you replace the inception network by clip, which they call FID clip, they actually produce a more reasonable ranking in terms of these particular models. Okay. So what about video generation? Everybody is talking about video generation. There are so many models out there, and one of the important issues in video generation is how can we evaluate these models. Again, somehow the FVD, which is basically a video version of FID, just replace the inception network with a pre-trained IS3D network, which are pre-trained on some action recognition datasets. But it's the same story here. You compute the pressure distance between these two video features. But there are lots of complaints by a lot of papers which says this FVD was actually have several issues, and there's some kind of another issue with FVD calculation, and there are people found the FID is very sensitive to the individual frames rather than the motions. Okay, so we actually have a recent study at CEPR, which we try to study FVD more carefully. We look at, for example, here is a reference video. This is a ground truth video. We apply some kind of median spatial corruption to the input videos, and we got FVD like 300. And we actually apply a very severe temporal corruption to the same original videos. But we get similar FID, but this motion look much worse than the original videos. Okay, and one thing we have done is we try to crop the video in two different ways. One is we try to infuse some spatial distortion, but we apply the same distortion to every single frame equally. So every single frame got distorted in the same way. We apply some spatial warping, and we also apply more like a kind of temporal distortion, which we measure something called spatial temporal FVD, which basically will apply different distortion with different parameters to each frame. So each frame get distorted in different ways. And then we try to, here are some examples. It's a bit it's a bit crazy, but this is our spatial temporal corruption. So it's supposed to look much worse, and it's just some spatial corruption, okay, which looks actually fun. One thing we found out is the temporal corruption actually does not affect the numbers that much. It only affects like sometimes only affects like, oh, this is FID, so FID is just we look at each individual frame, so it does not affect anymore. But if you even use FVD, it only increase the score by like 5% or 10%, 20%. So it's not a huge difference whether you apply spatial temporal corruption or you just apply spatial corruptions. And we measure something we call temporal sensitivity, which is basically the difference between these two metrics normalized by the first metrics, and you get this kind of percentage. Yes, basically this measures how much the FVD cares about temporal motions. And once we found out it's similar to this FID clip paper, is basically if you use a pre-trained network on like action recognition data sets like I3D, if you apply different motion blur, you get very low sensitivities, right? So it's almost doesn't matter. But if you replace that I3D with a self-supervised network like a video MAE, it actually can capture the motion degradation much better. Okay. Another thing we have been doing is we can actually inspired by this CLIP FID paper, we can we can assign a weight W to each samples, and we try to use that to minimize or maximize the FED metrics. And we can we actually found out you can if you use like a FBD, original FBD, you can reduce FED dramatically without even generating any motions. But it's very hard to do it for the video MAE. Okay. Yeah. I will present two case studies. For them, one study is StyleGMB. This is the original model, and this is one of their baselines, which was supposed to look worse. This is their paper, StyleGMB paper, a very nice paper, and this is one of the baselines. They replace something with LSTM code. And once we found out in the original paper is basically if their baseline looks worse, but the baseline's FED was actually lower than their methods. But if you replace the I3D, which based on the I3D FED, replace it by video MAE, you can actually see a very consistent trend comparing this model and the baseline model. So baseline that does look much worse according to the video MAE features. Another case study of the IGAN paper is this is the first 16 frame, and you can keep applying it. It's a kind of autoregressive, but the next frame looks much worse, but it was not reflected by much by the original I3D based FBD. But if you replace the I3D with video ME, it actually looks better. Okay, so to summarize it, the FED is highly biased towards the image quality rather than the motion and temporal consistency, and using self-supervised features such as the MAE, video MAE backbone model might improve its sensitivity to the temporal qualities. We also have a library called CD-FED, which can be quickly installable. Okay, to summarize the talk, I have worked with lots of different people, and they have different opinions of FID. So there are FID lovers, basically. We just talk about FID every week, and we just improve the FID by a little bit. And they also I also encountered some collaborators who are FID haters. If you cannot even mention the word FID in the meeting, so they will go pretty pissed off. By the way, so they will say, oh, maybe we should stop using all these metrics, and it's all it doesn't matter. You should look at the pixels, look at the video results by ourselves. I kind of in the middle. I feel like we should use metrics with careful implementations. Even the same metric, same formulation, different implementation can produce quite different results. And maybe we should use more than one metrics than FID. We can look at other metrics and including user studies. And maybe if we care about some particular task, like editing task, we should evaluate on the downstream application rather than the original models. Again, thank you. Yeah, thanks.
For the questions, can you work up to the microphone in the middle? Thank you so much.
Thanks for the excellent talk. Could you talk a little bit more, for example, other applications like non-RGB image generation, for example, satellite images where you can have like 3 channels to begin with. Have you used FID in this condition? What could you talk about this situation, please?
Yeah, so you're asking a question about can we apply FID to non-RGB natural image data sets, right? So
what are the metrics would you recommend?
Okay. But I think I don't have a good answer, but I think the answer I know is we probably shouldn't apply FID, the original FID. I mean, if you have a backbone model from that domain, let's say someone train a classification network on medical imaging data set and you apply it to medical imaging generation tasks, maybe that's quite reasonable things to do. I will be very cautious about applying the original FID without modification. Yeah.
Thanks again for the nice presentation. I want to ask if you could put like a few more words on those self-supervised learning features. Like we see, for example, video MAE has a more robust feature, probably. I don't know. Have you maybe tried some contrastive learning model, for example, where they focus more on augmentations and maybe that's more robust on the, I don't know, video distortion, things like that. So would you add a few comments on that?
Yeah, I think we do have a more careful, more comprehensive study about other self-supervised learning methods. They usually, I think it doesn't matter that much whether you are using UMA or contrastive learning. I think usually if you don't use lots of labels to train the model, it works reliably well for the motions. Yeah.
Can you recommend some methods for that in the student's translation? Sorry for
Oh, you want some recommendation for metrics for internet translation? Okay. Let's see. First of all, I think you need to evaluate. You need to have a holdout test set with ground truth pairs, right? And then, I think it makes less sense for computing FID on image speech translation, although I also maybe computed some FID before, but you do want to check the alignment. You want to check whether the output has matched the input. If you have an off-the-shelf network, for example, you do edge to image, you can extract the edge again from the generated images and check whether it matched the input edge map. So that's often what we have done. We also do some user study as well. Yeah. Or you can also compute some like depends on your task. Sometimes you can compute some constructionals like LPIPs. Yeah.
this presentation, one question I have is that what is the value of the model scales that we are using for extracting the features? For example, we are using a lot of legacy features, probably because the bigger models are more expensive to improve, especially for evaluation between which GPU. Have you done any analysis on as you scale the model for evaluating FPD or FID? How does the sensitivity behaves, and does it get more calibrated with human-like perception? That's part one of the question. And second is, are you aware of any work where probably there is like an RLHF kind of a fine-tune, a large foundation model, probably multimodal, has been done to take, let's say, crowdsource 100,000 or 200,000 finally comparisons, and then come up with a metric or come up with a model that has been fine-tuned with that kind of data. We actually compute FPD or FPD like scores, FID like scores for judging the quality of generated data.
Okay, so let's see if I can remember the first question. Sorry, what's the specific thing?
Do you know the variation of the quality of these metrics?
Oh, okay, yeah.
As the model that is computing the features keeps getting larger and better.
So are you referring to the model become bigger? A bit bigger is the generative model or the feature extractor?
The feature extractor for evaluation.
I do think we also have some studies, but you use a larger model. If they have the same type of model, if you use larger model, it might work better. There are also some paper like DreamSeam, which they should replace the VGG network with more recent model. It does work better according to their perception study. Yeah, yeah.
And the second part was about, are you aware of some work where human evaluation, RLHF type of fine-tuning was done on some foundation model to compute the quality of generated?
I'm not aware of that. Yeah, maybe they exist, but yeah.
Or is that a good direction you know to do?
Could be, yeah, yeah. Yeah, I think that sounds interesting, yeah.
Let's thank Professor Zhu again. If we have further questions, we all have Professor Zhu come back on the panel discussion at 5:30.
Yeah.
Or sorry, 5.
Thank you.
Next, we have Sergey from Snap.
Need to do the Zoom, right?
I'll just. Turn it off for now. Just share this presentation. Everything should be taken care of.
Recording in progress.
This is all. Thank you.
Right. So I will also have some audio. I hope it will work. Hi, everyone. So I'm going to be talking today about video generation, and I want to tell that video generation has experienced really amazing progress this year, and maybe even yesterday we saw some, or even today, Gen 3 isn't even that cool. And okay. So yeah, so I wanted to go maybe from history, a bit of the history of video generation, and maybe we can see how it evolved. And when you go from history, you want to really go from history. So let's start from times long ago in a galaxy far away, and humans, they have always been generating some stuff. And maybe the first thing that I was able to find that humans have generated, this is hunting scene, which is 30,000 years old. And you can see that the quality is really not there. And but still, you see some action. It's not a static scene, it's a movie, somewhat movie. Then there is another action, which is maybe 2,000 years old. You can see much better quality, some perspective there. You can see parallel lines. You can see Alexander, and you can tell that the face is actually not well generated. So still quite a long way to go. And then we arrive at this kind of thing, which is, Europe and Italy in particular is covered in this type of things. Much better quality, a lot of action, there is something happening. So when all of this are somewhat images, or in some sense, these are images, but have people generated or created videos in the history before, let's say, the camera was invented? And again, it depends on what do you consider to be a video. So for example, is this a video? This is an animation of the head of a deer, again, some 20,000 years ago. Clearly some animation. So these are frames and very slow frame rate. Then is this a video? And this shows you a sequence of actions you need to do if you want to wrestle someone. That's 4,000 years ago, so pretty old. Finally, you have this, which is essentially a depiction of some wars, and there are 150, let's say, frames, 2,000 years ago. And finally, we arrive at this, which is just a flip book, not so old, 107 years ago. And there is a patent in UK on this thing. And so these are the first videos that were somehow drawn or created. And how about the first videos ever recorded? And contrary to opinion of many people, this is actually the first video that was recorded. This is a passage of Venus in some telescope, roughly 150 years ago. The quality is pretty bad, but you can tell it's actually pretty cool. Then this one, some 14 years later, way better. You see already people, human generation, right? Some people are moving, they're posing, much better. And perhaps this is the most famous one, but it's actually not the first. And when it was shown the first time, people were actually afraid that the train will come out of the screen and hit the audience. I assume you're not afraid right now. Sometimes have passed since then, so we're better educated. But anyway, these were videos first recorded. And now we, I think, can go and see the first videos generated. So, and we start with the past. The past, how video generation happened in the past. So maybe initially the first video generation works were gun-based, and when we were generating sequence of frames and we couldn't do it really well. This one, the first, maybe the paper video gun 2016. And you can see that the first line is actually arriving of a train. But like the video that was recorded 150 years before that is much better. So then fast forward, still not there. And soon people have realized that maybe with technology back then, you couldn't create compelling content for generic video generation. But what you can do instead, you can actually maybe solve some domain problems. So you cannot solve video generation as a whole, but you can solve maybe some of the problems. And I'm going to show maybe a couple of problems that were solved back then. And maybe the first one is I want to share our work on 2D animation. And, you know, I understand it's after lunch and probably difficult for people to attend to the screen. So let's try to answer a question here. Do you think this one is generated or this is real? So raise your hand if you think it's generated. I know there are some guys who are authors of these things, you don't participate. So it's generated or real? Right. So, okay, who thinks it's generated? All right, and others, I assume you're ready to cast a vote. What if I show you two videos? Do you think one of them is generated, or maybe there are two people doing exactly the same thing in exactly synchronous manner? Who thinks that one of these videos is generated? Oh, more hands, that's good. And then finally, if we show three, maybe it's okay. Something is odd here, and we'll stop the intrigue here and just say that the first one, we extracted motions, and we used images to generate the second two. And the framework is generic enough to support different objects, but still it doesn't support both objects at the same time. It supports either faces or human bodies or stickers or robots. And back then we were thinking what it is to generate motion. So we thought, what motion is? So we have a source image and we want to animate it. So how do we do this? We need to have some appearance representation that is fairly simple to do. And then we have driving video. So we want to extract motions from the driving video and somehow apply it to the source image and generate the final result. So how to represent appearance is fairly straightforward. You can have pixels or you can encode it into some space of some autoencoder. This is known, but how to represent motion is less clear. And so what we focused on is how to represent motion actually. And we thought that motion consists of three things. The first, as I move, things change in location. So I move my hand from here to there, location of my hand changed. And so if I put a point here, it moves again. So motion has changed and motion has happened and location has changed. So what else happens? So our orientation changes as we move the hand. If we plot the, let's say, the gradient to or normal to the edge of the hand, we see that the hand rotates. So there is some orientation changes that happens, and we can represent them with some local transformations around key points. And the third thing that happens is that as I move my hand from top to bottom, I hide some content, but also I introduce some content that you haven't seen, which is behind my hand right now, and then I move it to the bottom, you start seeing this content. So we need to do some in painting. And so we built a model that was 5 years ago, and we start with a source image, and we have a drive-in video. So we have two steps here. One is motion extraction, the other one is generation. And for motion extraction, we pass each frame of the video through the key point detector. This is unsupervised key point detector. It was not trained to predict key points. It was designed in a way that it predicts key points, and it produces heat maps. Then you can, through a soft argmax operation, you could compute the key point location. Additionally, it does produce, for each pixel, produces 6 values, which is a local affine transformation, which is a 2x3 matrix that does something like that. It basically keeps the parallel line parallel and models rotation and scaling. So for each pixel, we produce the probability that there is a key point, and also 6 values that represent the affine matrix. Then we can combine them in a way that we basically can subtract things and predict dense motion. And the third thing we do, we need to do some painting. So we need to define occlusion map. So once we define what the motion is, so the bottom thing represents the 3 things from the motion representation that we just discussed. We could take an image, encode it into some latent space, warp it according to the dense motion, just warping, multiply by occlusion map, and then we have an image generated. So the problem here is that we don't have really videos to train on. There are no 2 videos that have the same exact motion by different people in a pixel perfect manner. Something happened?
Yeah, the audio doesn't work.
All right. But luckily we don't really need that. We can take the drive-in and split it in 2 things, and we can use the drive-in as the target. And so, again, this thing is fully self-supervised. We don't provide information what this key point should be. And interestingly enough, these key points that we have learned in an unsupervised manner, sometimes they represent something, sometimes they represent the eye. Sometimes we don't know what they do, but if you start removing them, the quality of animation decreases. And this is a sort of animation we were able to achieve 5 years ago. We also open source the code. Many startups have been started because of this technology, also runs on device in real time. And right now it's good to see this technology revisited in using a larger model. But even 5 years ago, it was already done to a reasonable extent. And so I'm talking about the past of video generation to show you maybe some domain-driven solution that existed. And maybe the next domain-driven solution, I want to show you, again, using an example. So imagine you're watching a tennis game like that. And there are two players. And imagine that your favorite player is the bottom player, and you want the bottom player to win. And then we start looking at the exchange, and we see that actually the bottom player loses, and you want your player to win. So what can you do? So there are a couple of things you can do. So again, the goal is to make the player win. So you could follow the standard approach. You can reconstruct the scene, understand the strategy that the player should have followed, animate the players, render results. So to do this, you need to do like model 3D environment, physics. You need to support game AI, because as you change what the bottom player is doing, the top player should also change. Then you need to provide a sequence of commands, and then you need to decide on the viewing direction and render. So this is what the game engine is doing typically, and this is extremely hard to do and requires some time, probably not worth it if you just want one player to win. But is there a better way? And since I'm presenting this, clearly there is a better way, and our recent work called promptable game models. In this work, you can just give the system to the prompt, and the prompt is of the form, the top player is not able to catch the ball. So let's watch it again. So this is the exchange, and so it's right here. So right here, the bottom player needs to do something. So we actually need to change the strategy in this place. And what we can do, we can follow the graphics engine, or we can use our work and we can say the top player is not able to catch the ball. So as soon as we do this, our method understands that for that, you need to send the ball to a different direction. And the point is 1. And this is a sort of a game model, or we wanted actually to call it game engine, and the reviewers didn't allow us and rejected the paper because of that. So be careful about the naming, you know. We still feel it's a game engine, but we're also okay with a game model. And since it's a game engine, you could, or game model, you can change the pose. Oh, by the way, everything is generated. You can change the camera pose. You can also change the style of those players and many more things. So I want to maybe give a little bit of detail of how to learn this game AI, how to let the system execute goal-driven commands. So imagine we are in an LLM setting and we want to train the system so that when I ask her to win, it knows what actions it needs to do to win. So how can we do this? Imagine we have a video annotated with this prompt, and the prompt is the bottom player sends the ball to the left sideline, and the top player is not able to catch the ball. So this shows you a game environment. So we can run the results through tokenizer and generate it using an LLM. But also what we can do, we can mask some part of it, and we can add pose and player location, which we also can mask. And now you can think of it as the bottom player needs to do something so that the top player is not able to catch the ball. So basically by doing this masked learning task, we ask the model to produce a strategy to win. And in that case, masked learning can learn sequence of actions. And what's interesting, the model is also able to, provide fine-grained details. For example, here we say the player hits with a backhand, and backhand is this kind of movement if you're not playing tennis, and you see the player is doing backhand twice. And if we arrange the same sequence, but we say the player hits with the forehand, which is the other movement, and the player hits with the forehand. So this I wanted to show you some cool things that were possible to do in the past. But present is actually much cooler. In the present, we can do what we have done in the past, but much better. And maybe we can go into that right now. So, some also artifact from the past, generative adversarial models, and they generate an image in one single step. They go from noise to an image by just doing one pass through a convolutional network. Diffusion model, instead, they are solving a task in many different steps. They are going from a lot of noise to slightly less noise, and kind of intuitively, this task is simpler because it's harder to solve a difficult task in one step rather than if you have 1,000 steps. And so that's why we brought this amazing recent diffusion models that are latent diffusion models. And one question a reasonable person would ask here, okay, we can generate these images, right? But video consists of images. And can't we just generate frames of the video using these models? If the images are so good, why don't we just take these models, adopt them somehow, so that they will be generating frames of a video? it's really, why not? Really, it's a not too bad idea. And people have tried this, so there are some models. You probably have heard of Stable Diffusion, I assume. But I'm sorry. But there are like a couple of models. So EDFI is from NVIDIA. So you can take this model, take UNet, and insert some temporal layers into UNet. When doing that, you will be able to generate videos like that. And you know, you inserted temporal layers into UNet, and you see how Panda is inserting a pizza in their mouth. So maybe it's cool, but is this really the state of the art? And if you do the same with Stable Diffusion, there are several attempts. I mean, they're good works, but in any way, there's something wrong here, right? That we cannot really reuse image-based models to generate video, and you might be wondering why. And so if we look at how diffusion or denoising process is done, we start from, this is in image domain, we start with image with a lot of noise, and through sequence of denoising operation, we go through less noise. And then this arrow is a learned denoising model. And if you think about denoising, as we discussed right now, GANs, they go from a lot of noise, no noise. And we consider this as a hard thing to do, going from a lot of noise to little noise in one single step. On the other hand, if you do, you know, no noise or very little noise to no noise, this is a very simple task to do. And finally, if you go from, let's say, noise and slightly less noise, this is just right. Imagine like you are learning some advanced math, and if it's too advanced for you, it's hard. If it's too easy, it doesn't probably make sense. So you want to always kind of learn stuff on the boundary. And this is a very intuitive explanation, of course, and doesn't have to be right, but it's a nice one. So a lot of work is done to find the right noise schedule. How to denoise, what's the steps, how each step should denoise. Because this is kind of one of the key things in training those models. And if we look now in the videos and apply the standard noise that we apply for images, we'll see this. So this is a video with standard noise from images. So the noise is exactly the same as in the top row. And the goal of the model is to denoise that. How to denoise that? If we just take averaging of these frames and we apply, it's not playing or playing? Playing pretty slow, right? You don't see the videos, right? Yeah, somehow it's extremely slow. So it's actually, I'm going to show some cool videos. It's sad. Anyway, so if you take these videos and just apply temporal averaging on top of the frames, you can denoise it almost entirely. So you apply some very simple denoising trick and you get video denoised. So there is not much to learn left. And so there is little difference, you know, here in these videos. And so if we use image models to do video generation, it seems that we are making the task quite simple and the model doesn't learn much. So instead, what we can do, we can substantially increase the level of noise. And in the paper, we have a derivation how much that should be. And then if you apply temporal averaging, you actually get a reasonable amount of noise. So the task is not becoming easy. So that's one thing. And another thing that is particularly maybe bad about image models is that there are different generation paradigms. One of them is you generate video frame by frame. So what you do, you run your entire unit to generate a frame, and then you run it again to generate another frame. So you run entire the denoising to generate each frame. So it's pretty slow. And then these two blocks, they communicate only through temporal layers that are inserted in your unit. Instead, there's another way to do this. You can denoise your video entirely as one single concept. First, you need to compress it because videos are quite big. And then you can have a block that does special temporal denoising. Then you can decompress it and generate video at once. And this is joint spatial temporal model. So, and recall that the first one, you have to run diffusion 1,000 times for each frame, and then you do it as many times as you have frames. So there are issues with scalability there. And so scalability is the primary requirement for quality. So the more you can scale the model, it's not easy, but it usually helps. So the model on the right is better scalable. And now we go to Snap Video architecture details. And Snap Video is a word that will be presented in the main conference. So we have a video, we split it into patches like that. So we just cut the video into patches. Then we take each patch and compress it using some patches to pixels. So we take a patch and compress it to tokens. Take another one, compress it to tokens. So we have patch tokens. Then we can take our transformer, it's based on FIT transformer. And through a cross-attention operation, we could compress attempts to all patches jointly at once. And then we can add this text encoding and other common diffusion things that we add to every model to generate images of 3D or other. And we can run the transformer and run the denoise in many steps. So after it's finished, we can decode it back to patch tokens, and we can run, again, reconstructed patch by patch in that manner. So why does it scale so well? So first of all, this is a joint block that processes videos as one single thing. It processes space and time. Not only can it learn better the motions, but also it's much more efficient in terms of scaling. Second, this is compression. It takes a lot of information and compresses to little information, and the denoising process is run on this compressed representation. And this is decompression. It takes this little and lifts it back to patch tokens that can be decoded back to patches. And maybe now it's time to show some results. So this is Gen 2. I know we saw like Gen 3. Gen 3 is better than this, but this is Gen 2. It's a video. It's just not very dynamic. So this is another one from Pika Labs. And again, this, I think samples were made roughly half a year ago. So clearly things have changed and those methods have improved. This is another model, and you can clearly see that the quality of pixels is relatively high, but the quality of motion is low. So horses don't do this kind of stuff. And this is ours, so you can see motion. There are other things we can do. We can, this is latent video, latent diffusion model, and this is ours. Again, these samples have been made more than half a year ago, so right now probably things are different. And this is a dog wearing virtual reality goggles. This is our dog, so you can see motion is much better. And then maybe what we found out is that the same approach can work also for audio. So we take the same transformer, but instead of having like video and image processing things, we add audio things in a pretty much same way. And we change slightly the architecture. And then we run diffusion, and then we can decode. And this is the recent work called GenAudio or GenAu, which is a word in German. And maybe I'll show you some examples right now. No. How can I play it with here?
Let's try playing.
Okay, so this is a recent work, it's an archive, or it's not an archive actually, but there is a website. And it's 1.2 billion model with quite superior sound quality. And also one part that we are also trying to make public is that is currently the largest data set of sounds with captions. So this was the present, and the present is very exciting. And maybe about the future, I have only some words to say. In particular, I want to maybe say that in the future, maybe you will not need a camera. Maybe everything you need is just a good video generator, maybe that runs on your device. And maybe you will be able to generate videos such as this too. And here we have an option. We can play. How much time do we have?
Continue.
Yeah, I mean, so if you want a space invasion video, raise your hand. All right. How about panda? Right, people love pandas. Let's play panda then. But I'm worried that you won't see frame rate well. All right. So it seems that future video generation is extremely exciting. So we'll see probably a huge number of models appearing. There will be different ones. Maybe some of them you will build, maybe some of them we will build, but it's nevertheless quite exciting. And I think that's the last slide that I have. And if you have any questions, happy to answer them.
Maybe I think we can take a couple of questions at most. If you have any questions, please come to the microphone in the center.
Have you, do you, do you think like the video generation, there will be a thing like the model training, progression, like that, all those kind of complicated, but more like engineered rather for research kind of product?
I think it's already engineering. It's like there is some research, but it's just hard to scale them, and it requires a lot of architecture, infrastructure work. At the same time, I think our relative happened after GPT-3 moment, and I'm not sure for videos we arrived at that moment. So maybe we need first GPT-3 moment for video, and only then we can do a relative and other more sophisticated things. Yeah, go ahead.
Thanks for the very nice presentation. I'm from the OFC. I have this question that how can we make sure about the physics-based conditions, like the lighting direction, its shadow, and these kind of stuff when we generate the models? Because I've kind of seen that much of the research that they care of these physical photorealistic conditions in the generating process.
Um, So the question is why, what about physics? So this is, I think, amazing question, and I think there are two schools of thought here. The school of thought number one, that thinks that as long as you have seen enough videos, you have seen any interaction of the object with the world, and you have seen any possible physical interaction. And then if you follow that school of thought, you will say, I don't need any equations of physics integrated in my model because I can learn everything from the data. So the other school of thought says, why do we need such huge models if we can use some differentiable equations that will simulate, for example, how water moves, and perhaps this will allow our model to train faster and it will be more efficient. And if you follow that school of thought, you need to start doing this. I think myself, I'm more kind of on the end of the first school of thought, maybe because I didn't like physics at high school. But I think it's just about the data, and we can model not every phenomenon. Many things are difficult to model. Yet at the same time, we're starting projects in our team about both like scaling the data, but at the same time, we're looking at physics. So I think we'll see what the future will tell. At the current moment, it's hard to tell what would be the right way until someone just shows it.
Thank you so much.
There is one or two more. I don't know how much time we have.
Yeah, sorry, I think we're probably in big time.
Take one more or no?
I think, yeah,
All
I
right.
think, sorry.
But I will be around, so
Yeah.
yeah, sure.
Maybe we could take this offline. Thank you again for giving this exciting talk. Next, we have Richard. And next, we have Richard Zhang from Adobe. I think it's showing up, but so just press this. Okay. This is also shared from Zoom as well. From you.
Oh, Zoom, there's a
Yeah.
Zoom link.
Yeah, so there's a. Send it out this morning. Yes. Right. Sure. I think it's just, I'll test it. Oops. I think the title is Magic Workshop Speaker Instructions. If I get it, I would just forward to you. So again.
You need the Zoom?
I think there's this also remote. So.
Can you send it again? Just
Yes. Or can I share from somewhere else? Just yes. Oh, there you go. Okay.
all right, there we go. Okay, so it's working?
Yeah.
Audio's working?
Yes.
Okay. Okay, good. Get started or?
Yeah, let's get.
Okay, good afternoon, everyone. So this is incentivizing opt-in, enabling opt-out for text-to-image models. So there's been astounding progress in image generation. Right now, there's a plethora of different models that are serving as the backbone of different content creation workflows.
But these models, of course, don't come out of thin air. Ultimately, they're a reflection of the underlying training data that went into them. Now, training data, of course, ultimately comes from people or contributors. Now, right now, these people are unfortunately cut off from the modeling process. So while us researchers and founders are excited, there's been a lot of pushback. There's been ongoing legal battles, Hollywood strikes, and digital artists are pushing back, noting that their work is being used without consent and without compensation. So what can we do in this case? Well, in this work, we'll be looking at reconnecting creators back to models, and we look at this from a few different lenses. So first, we believe that in many cases, creators should have the right to opt out of a model. Unfortunately, that operation is extremely inefficient right now. So we're looking at this idea of ablation, be able to efficiently edit a model so that someone can pull their personal images or their concepts out of the model. Next, we look at this task of attribution. That is, given a synthesized sample, we'd like to be able to find out the specific training elements and the specific training elements that made that synthesized example possible. So first, we'll do a little quick overview of something else called customization. And this allows people to take an active hand in the creation in the model creation process by adding their own personal concepts within the model. Okay, so this is work that we published at CVPR of last year. The first author is Nupur Kumari. It's called Custom Diffusion or Multi-Concept Customization. So what we started with this project is that text image is not perfect. So if you take a pre-trained stable diffusion model, ask it for a moongate, this is what you get. You ask for another sample, this is what you get. Now, these actually aren't moongates. This here on the left is a moongate. It's like an Asian architectural element. So not only is the moongate not in the model, there's also other things like your personal pets, objects, or perhaps your own personal artistic style is not going to be in the giant pre-trained model. So in this project, we're looking at how can we efficiently add concepts into the model. Okay, so we'll do a quick overview of diffusion models. There's a fixed floor process, which adds noise, and a learn denoising process, which removes noise. And the training process is you draw images, add noise, and then ask a network to predict that noise, and progress is measured with L2. Okay, so how can we add someone's concept? Well, we can simply replace the large-scale training set and fine-tune it with a small personal database. And this ends up working really well just out of the box. So here's a pre-trained model that we showed that didn't work. If you tune the whole model, you start getting something like this, like you start getting a moongate. And what we found is that you don't have to tune the whole model. That's going to be very expensive. What you can do is actually just tune the cross-attention layers. So basically, you can get strong results just with 3% of the network. So from here, we started having some fun with the system. So my co-author Junyan has a very cute pet dog, Stark. And so we gave him some headphones. Nupur has a toy plushie. And so we rendered it with some kind of a watercolor style. And my colleague Aaron Hertzman likes to do a lot of drawings on his iPad. So with his permission, of course, we trained a customized model on that. And around this time, we were part of an initial cluster of initial works. So there's these other initial very influential works called Textual Inversion and Dream Booth, which many of you I'm sure are familiar with. And between our three works, we kind of discovered, you could think of these as kind of spanning a space of kind of what parameters that can be tuned for this customization task. But they kind of started getting this subfield going. One kind of aspect that we uniquely pushed on at that time was exploring the composition of multiple concepts together within a model. So the idea here is we have drawings from Aaron, and we have a wooden pot from Nupur. How can we perhaps add both of these into the model at once? Or perhaps we want Stark in front of a moongate. Now, the naive thing, which is perfectly reasonable to start off with, would be to do joint training using the fine-tuning procedure. The problem with that is that it's inefficient to train every single combination of concepts that you may want to compose together in an image. So what we explored is something more efficient. We explored doing this in a modular fashion, be able to train separate customized diffusion models for every single concept, and after the fact, having a more efficient method of merging them together after the fact, using some optimization-based method. And by doing this, we can generate this wooden pot in this art style. We can put Stark in front of a moongate. or put this QCAT inside of the wooden pot. Okay, now this was all last year, about a year and a half ago. This is an extremely active research area. So there's probably some papers I missed on this list, but there's a lot of work pushing on making this process faster, really improving the multi-concept aspect of these generations, as well as improving the storage capacity, making things smaller and more efficient. So I encourage you to check out all of these works as well. Okay, so far we've talked about adding concepts into a model. But of course, the model already has a lot of concepts already in there, and these include things that maybe we don't even want. So for example, there's personal concepts like Grumpy Cat. That's a meme, but that's actually someone's pet cat. They may actually have some kind of copyright or ownership over their likeness. There's of course copyrighted content like R2D2. There's artistic styles from artists that are gone, like Van Gogh, but also living artists today, which who may not have wanted their kind of personal styles kind of in these training sets. And then models also have this kind of strange behavior where if you have a lot of copies of a training image, it starts really memorizing those training images and just emitting that image over and over again, really collapsing to it. And that may not be desired either. Okay, so these kind of issues or bugs in the model have been discovered, and there's been kind of publicity around why these behaviors are bad. And so in this work, we're looking at asking, can we actually remove copyrighted or sensitive concepts that are already in a pre-trained model? Okay, and so this is work that we published called ablating concepts or concept ablation. So again, let's start off with a naive baseline. So if you were to want to do this task, the first thing that you would try, which I think is very reasonable, is you could go back to the training set, find all the images that are relevant to the concept that you want to remove, such as Grumpy Cat here, remove them and retrain the whole model. And this would definitely work. This is a perfectly reasonable place to start, except the problem, of course, is that it's extremely time consuming and computationally intensive. Maybe you can get away with doing this once, but if you have to remove something else, you have to do it twice and over, that's going to be very completely untenable. So what we want to do is be able to quickly tune the model like we did before, except instead of adding a concept, we'd like to remove one. So let's start with a potential solution. A diffusion model is trained to minimize L2 loss between the added and predicted noise. What if we just maximize that instead? Okay, let's give it a try. So here's a pre-trained model generating a Grumpy Cat. Here's a nearby concept, just an unrelated cat that we'd like to preserve. So if we maximize L2 loss on the target concept, we get this. So we've removed Grumpy Cat, which is a good thing. But unfortunately, we've also blown out the nearby concept of this innocent cat, right? So this nearby concept has also been changed, which is an unwanted property. And beyond that, if we continue to train, the training will end up diverging. So that's also unwanted. Okay, so how can we get past these problems? We'd like to have a stable training procedure that removes the target concept, but keeps the nearby concepts unchanged. So what we'll do here is look at this from a distribution matching perspective. So instead of maximally diverging away from the target, we'll look at trying to overwrite the target with something else. So if we prompt the model with a photo of a Grumpy Cat, what we actually want to come out of the network is a photo of something like a generic superclass, for example, a photo of a cat. Okay, so we're going to overwrite Grumpy Cat with just a generic cat. Okay, so kind of a cartoon illustration of what we're going for here. So we're trying to move from the green distribution into the blue one. Okay, so our model here is we can prompt the model with photo of a Grumpy Cat. And from there, we can also prompt it for photo of a cat. Each of these is going to predict a noise pattern. And then we can take the bottom branch here that comes from a cat and use it to overwrite the top branch of Grumpy Cat. And we can also add a stopgap here because we want to minimally corrupt the bottom branch, that's why that's there. So in essence, we're using the network to quickly retrain itself. Okay, so here are some results. So on the left, we have our target concept we'd like to remove. On the right, we have our nearby concept that we'd like to preserve. Okay, so here we've, again, removed the target concept, which is desired. And now by doing this, the nearby concept is preserved, which is what we wanted. Okay, so we have something that is workable. We're going to try it on a whole bunch of other examples now. So one thing we can start off with is some Disney characters. So there's R2-D2 in Stable Diffusion. There's Nemo, slightly creepy Nemo, but it's Nemo in Stable Diffusion, and we're going to try to erase these. So we get a more generic looking robot and a more generic looking fish after erasing. We can then apply this algorithm to erasing memorized images. So here we have n-gram lots, which is this famous example of an image that was repeated in the training set, and then the network is happy to regurgitate it. So we can add some diversity in this generation rather than just collapsing to that single image. And here on the right, we have a video game cover. Okay, and next we can also look at artistic styles. So Van Gogh, for example, has these very signature wavy lines. We can try to replace that with kind of a more generic concept, just a painting. So instead of prompting for Van Gogh directly, this is just prompt, we overwrite it with a painting. And we can do the same thing with Greg Rukowski, who's a living artist who started just being used in these prompts over and over and over, kind of as this was kind of a phenomenon when these models started popping up. Okay, so thus far, we've been looking at erasing specific concepts. We can actually take this a bit further. Okay, so in this case, a pre-trained model may have two different concepts, for example, kids and guns, that on their own are actually perfectly reasonable to generate. But a generative model, of course, is happy to compose them if a user wanted to. And then we start straying into territory that we don't want to be in. We don't want to necessarily generate photos of kids holding guns. Maybe the gun can be pointed towards the kid. We would prefer to avoid that. Now, previously, in order to avoid that, you would have to basically remove all the kids from the model or all the guns. But that's really a really heavy-handed approach to this very specific problem. And so with our method, we can actually target just the combination while leaving the original concepts more or less untouched. So here, after ablation, we can still generate kids and guns separately, but what we're targeting is removing their combination. And so that works. But of course, we note that if you look at the results, there's not a perfect disentanglement here. So there's still work to be done. But to us, this was exciting because this is actually going beyond just erasing one concept at a time, which theoretically you could just do by cleaning up the data set. This is something actually targeting a specific behavior that's kind of emergent in generative models. Okay, so in this work, we looked at overriding a network with itself, but there's work to be done. So as you saw in some previous results, there's not going to be perfect disentanglement. And there's also really hard questions to answer, like, is something really removed? So if you remove Van Gogh, but you prompt the network with painting in the style of the guy who cut his own ear off, or if you look for a Starry Night, things like that may still be in the network. And it's hard to kind of really evaluate if the influence of something has truly been removed. So there's still work to be done there. Okay, in this section, we looked at enabling users to opt out of a method, of a network in an efficient way. Of course, that's not ultimately what we want. We don't want everyone pulling their data out of the models. We want everyone to be participating in these models because these models are a good thing, right? They're enabling a lot of creative workflows that otherwise wouldn't exist. Okay, so what we'd like to do in this next part is actually incentivize people to actively participate in these models. And so I think a big part of that is this problem that we're studying, which is called data attribution. Okay, and this work was led by Shengyu, who was in the previous slide. So the idea of data attribution is, given a synthesized example, we'd like to be able to find the specific elements in the pre-training set that had high influence in making this generated example possible in the first place. Now, this is actually a very challenging problem because the ground truth here is fundamentally unknown. You have millions, perhaps billions of images. They're all munched together into a set of weights. How can we really disentangle the contribution of each one of these training images to find which one was actually the more important one, or the groups of images which are more important? So to do this, we need to somehow intervene in the training process. We need to somehow intervene, and by doing that, we can study the relationship between training images and generated images. And luckily for us, in the previous two projects, that's exactly what we were working on with customization and ablation. So in our initial kind of attempts here at this problem, we've been trying to leverage some of those insights into this attribution problem. So what we started off with was this idea of attribution by customization. Okay, the idea is that you can generate an image from a pre-trained model, but you don't really know the influencers that were underneath. But you can tune the model with custom diffusion, and you can generate this new building. And this new building, it's not only influenced by this exemplar, but we know that it's definitely heavily influenced by this exemplar just by construction. So we can get a ground truth influencee pair in this manner. So in this project, we set out and went ahead and built a data set using this kind of very simple insight. So here we're curating an attribution benchmark. There's two parts of it. One is very artist-centric. So the idea is you query for kind of an artistic image with a generic prompt. You can instead fine-tune it towards a specific artist, for example, Fernando Botero, and we grab these collections from Archive. And by doing that, we get images that were that have the style that's been inspired by this collection of images. So that's one section of our data set. The other is object-centric, which we looked at with this building. So we can grab random images from ImageNet and train on them as exemplars. So in total, what we ended up with was we got 18,000 custom diffusion models. And from those, we gathered about 4 million samples. So we got kind of a medium, large scale data set for doing attribution through customization. And so what does attribution mean in this context? Like, how do we actually leverage this data set? Well, now we have this ground truth pair between the exemplar and the output image. We can get other images, like 100,000 other images from the data set. And then we can ask the question, which of these potential images do you think was the exemplar? And a good attribution algorithm should pick the one that's the ground truth. Okay, so essentially we've now converted a really difficult attribution problem into a more manageable retrieval problem, which we have tools and kind of a language for dealing with. And so the first thing we can do is evaluate different feature spaces to see how well aligned they are with this attribution problem. So let's do that here. On the y-axis, we have the performance on the artistic models kind of subset of our data set. On the x-axis, we have the object-centric models. So up and to the right is good. So here we have a whole bunch of different pre-trained feature spaces. On the right, we have Dino, Moco, VIT. They're really strong for object-centric models. SSCD and Aladdin are kind of specialized feature spaces for copy detection and style descriptor, but they don't really do as well. They're on the kind of bottom or bottom left. And we see that Clip here is at this point getting really middling performance. But this isn't the end of the story. Because we have a data set, what we can do is apply contrastive learning techniques towards kind of calibrating each of these feature spaces so that they're better aligned with this specific attribution problem and data set that we've created. And after doing that, we see each of these methods have different size improvements. And in particular, Clip itself it seemed actually primed for large improvements with just a little bit of linear calibration on top. Now you see there's also this kind of trade-off. We have a trade-off between these two different axes, the artistic model's kind of attribution and the object-centric attribution. So they kind of form a Pareto front that hopefully future methods can do better on. Okay, so we'll show some custom diffusion results. So here's a pre-trained feature space of Dino, and after calibration, in this case, the ground truth went up. And we can also, even though this was just trained for custom diffusion, just for fun, we can also test it on large-scale pre-training of stable diffusion as well, and we get these results. Okay, so in this section, we looked at the attribution problem, which was really hard to figure out what ground truth is, but we established ground truth through customization. one issue is that the pre-training set, however, is ignored. So in this kind of final section of the talk, we'll try to discuss how we can take steps towards really targeting that pre-training set. So for here, we're really inspired by previous work in the area kind of focusing on data attribution for descriptive models. And the idea here is that instead of adding, like what we did, you can think about removing data instead from the pre-training set. So there's this concept of Shapley value, which is a kind of landmark concept in economics. And one embodiment of that in the machine learning literature is by Feldman and Zhang, where they train on random subsets of the training set and analyze that population of models. And then there's also this whole line of work on influence functions, which is really interesting, that looks at up or down weighting a training example, making linear approximations so that you can evaluate its effect on an evaluation sample. But one difficult thing with all these different works is that really, if you look, it's really challenging to evaluate attribution with the large training set. We're still stuck with kind of the original problem that we're dealing with. So one kind of way of doing evaluation, we can call it counterfactual evaluation. So what that means is, given a training set, you can synthesize an image from a model that's been trained from that set. Let's say we have some sort of method to identify influences. We won't say what yet, but we want to evaluate how good that method is. It makes sense that if the right images were identified in that process, if we're able to actually remove the top K influencers and retrain the model, this is called a counterfactual subset. Like, what happens if we remove these images? You can create, let's call it a counterfactual model, right? And if you successfully identified the critical training images, removing them and retraining into this counterfactual model should actually destroy the generation. And you can kind of formalize what it means to destroy the generation in a few ways. One is you can check the DDPM loss of the original synthesized example in your counterfactual model, or you can ask the new model to emit a new image with the same noise seed and basically assess the difference between them. And so in our paper, we have very systematic studies of that. Now, one issue here is that this is extremely expensive. So basically, for every single synthesized image and every single method you have to evaluate, you need to retrain a whole model from scratch to get kind of this gold standard result. And that's part of the reason why this kind of study has not really been scaled up. So how do we kind of get around this? Well, in our work, we decided not to. We just had a very brave student, and he just said, let's do it. So let's actually run this evaluation, as crazy as it is. But of course, we have to keep ourselves at somewhat modest data set sizes. So we did that for this project. Okay, so how do we actually find these influence sources? Well, let's think about a brute force approach towards approximating this kind of gold standard evaluation metric. So one thing you could do is actually take a whole bunch of different subsets of the training set, train models from scratch, and analyze that population of models. Now, that may work at the limit, but just looking at this diagram, you can already tell that that's way too expensive. You can't train that many models of the training set, and you certainly can't be training them all from scratch. Okay, so can we do something that's a little more efficient that still gives us a good approximation of this? Okay, here's what we came up with. This is called attribution by unlearning. So our idea is that we can take an unlearning method similar to ablation that we showed before and tune the pre-trained model to forget about the synthesized image. That is, we tune the model so that it can't represent the synthesized image as well. And then we can see which of the training images were forgotten by proxy. And our hypothesis is that these two things are going to be related in a causal way. Okay, so we forget a training image, and then we evaluate how much each of the training images was forgotten. Our learning procedure, I can quickly sketch it out for you. We maximize the loss on the synthesized point, but we need to have some sort of regularization. That is, we want to not stray too far from the original training set, so we can try to minimize loss on the original training set. From the continual learning literature, an efficient way of making a quick approximation is doing a local second order approximation, which is called the EWC loss from this paper listed below. Okay, so this is work that we just recently put on arXiv last week. called attribution by unlearning synthesized images. Okay, let's look at some results. So here are some, here's a generated Cocoa image. Here are different attributed results from ours as well as baselines. They all look kind of reasonable, especially the top two. So what we need to do is this counterfactual test. So we're going to remove, so the data set is about 100,000, a little bit more than 100,000 images. We're going to remove the top 500 attribution results and retrain and regenerate here. And so that represents about 0.4 of the data set, 0.4% of the data set. Here's our result. You can see that the bus is completely changed from the original generation, while for baselines, you get more or less the same bus with some minor differences. So this kind of indicates through this counterfactual evaluation that we identified the critical 0.4% of the data set that really heavily influenced this generation. I can just show one more example of the skier. Here you notice that our method finds skiers that have somewhat more consistent pose and appearance, as well as the number of skiers. But really the important thing is to do is counterfactual test where, again, we are removing the images we identify causes a larger deviation from that generation. Okay, here we can just show some additional qualitative results on different objects. And finally, we can show kind of more specific application. So right now we're doing everything at the image level. We've had some small experiments looking at local attribution because there's nothing really preventing you from running the same formulation, but just on a crop or a segment of the image. And then you can do attribution on different elements of the image instead. Okay, so for this data attribution problem, we looked at customization to add one in. That establishes some notion of ground truth, but we actually found it has limited generalization to general pre-training. So we instead looked at unlearning to leave one out. We found that you can efficiently unlearn a synthesized sample, evaluate the effect on the training samples, and through a counterfactual evaluation, it seems like this method is pretty effective. Now, one problem is that it's still expensive. You still have to evaluate that unlearned model on each of the training images. So I would say right now it's not very practical for prime time or actual use. So this leads to potential future work, more effective approximations, and something we haven't really gone into is group effects, how having two kind of concepts together may actually change the behavior of a model. So that's something that should also be interesting to look at. Okay, so in this talk, we looked at different methods of reconnecting creators with models. We'd like to enable people to opt out if they wish to do so, but what we really want is to incentivize and have everyone collaborate and be able to participate in and opt in. Okay, here are the works that I discussed. Please refer to them for more details. I'll especially call out Chengyu and Nupur, who are the lead authors on these works, as well as thank my wonderful collaborators, including Junian, who spoke earlier in the session. And with that, I'll also thank you.
Maybe we could take a couple of questions from the audience. You could use the mic in the middle. Or-
Well, one thing very key problem. Okay, can you hear me?
Yeah.
So is it the diffusion models basically make it more challenging? Because I can imagine that a QBA right generating model, maybe because it is already building some clusters of the data in there, maybe it is more easier to solve this attribute like problem with those kind of models than the diffusion model itself.
Got it.
It's a classification, you say, okay, this is a cluster, and then.
I see. So I'm understanding, yeah, I think with BQBAE, the clusters are kind of more for low-level compression of the image. It's still really difficult to do attribution at kind of a higher level, like why is this like arrangement of pixels being generated? That's also still difficult. What we're hoping to do is have a general formulation that applies across generative models. I mean, of course, today we're all doing diffusion models. Yesterday we were doing GANs. Tomorrow, right now, there's inklings that all regressive models are gonna take over. So we want formulations that are kind of general across these different types of architectures. And of course, there's going to be points where you have to take advantage or kind of tailor the algorithm to specific kind of elements of what you're doing. So, for example, for us, a strength of diffusion models is we can evaluate DDPM loss and use that as kind of a proxy for how well an image is modeled in the data set. And for something like for GANs, that's not going to work. Maybe for autoregressive models, it will. So there's going to be kind of different things that do apply across different models and things that don't.
How many concepts do you think that you can remove from the model before destroying the model?
Yeah, that's a great question. So we, I think we had the study and in the paper, I don't recall. But definitely, yeah, we had a study where you keep removing and you see how well things are preserved until the model breaks. Yeah, I'd have to refer you to the paper, but my initial kind of recall is maybe about 10 or 20 or so. At some point, you probably should just retract from scratch. Yeah.
And the things from the model that were used that when there is a total sensor system, the final model have some problem generate worse images. Do you think that this problem could be taken in some way in the future?
Sorry, I didn't quite.
When you remove some images from the data set, for example, for simple diffusion to get one that is less used by the community, generate worse images than one that use larger data set with process.
Got it. Yeah. So if you start removing like all the concepts, 90% of your data set, yeah, your overall quality is definitely going to get worse. Yeah.
Let's thank Richard again for this insightful talk. Thank you so much again. We'll see you again at 5.
So I think we're going to take a 10-minute coffee break. We'll reconvene at 3:20. Yeah.
好，现在你开一遍。我想我就我到底要看那个怎么摸这个 announce page 的吗？你是已经退出了？
我应该关掉这个结束。
再 join。
先摆一下那个。Is she still around or? She's gonna be remote actually. Oh, okay. Yeah. 哦，这边声音调大点，这个调声音。
Yeah.
I think Yunzin's online actually.
Hello. You hear me?
I am not sure actually. I think we need to yeah.
Can you hear me?
Hello. Yeah,
Hello?
I think Yunzin, you're online already. So
Yes.
can you hear us?
I can hear you. Yes. Can you hear me?
We don't hear your voice.
Oh. Can you hear me now? No?
I don't know. But that works.
Hello. Can you hear me? Let me rejoin.
Hello.
Hello?
Hello.
Can you hear me?
Hey. Yes. Can you hear
Yeah,
me?
yeah, I can hear you on my
No.
laptop, but
Oh.
I can hear you on my laptop, but
Yeah.
cannot hear you on site at the conference site.
I think I heard a
Oh.
hello, but that it's not there anymore. Oh, it's you. I say. Hmm.
Let me log out and rejoin.
Hi.
Yeah, it might not be your problem.
Captioning and deaf, and it's easier for you.
Oh, I see. Okay.
Are you using Zoom?
Yes,
Yeah, Zoom should have a closed captioning thing.
I'm not sure how I could enable that. Closed caption. There you go.
Yeah, I see it. Thank you.
我Zoom 能听，我 Zoom 能听，但是
我这边没有听见。Okay.
会上听不见。
Okay. I think I.
Hello. Hello.
Oh, so it's my this.
So we don't think it's your problem. I think it's the device here. We do hear you in the Zoom, but Sam, can you hear me, Sam?
Yeah. Can you? Yeah. Can you help cast? You speak something?
Yes. Can you hear me?
320. Yes.
So yeah, I can hear on the Zoom.
And can you see my screen? Share?
Yeah, we can see your
Your
screen.
Okay.
It's gone now. Well, no, we can only see you, but not your
Oh.
slides.
You don't see my screen? You don't see my slides?
Yeah, we can see your slides on the Zoom, but on site, it's. I can show you. I can show you.
Oh, interesting.
Yeah, the device has some
Let
problem.
me try jumping out and jumping back again. Oh, you can hear me from there,
I
right?
can hear you in the Zoom.
Lead meeting. Let me assign you as host. Okay.
Can you hear me?
Yes, I can hear you.
Okay. What are you if you close join with computer or audio or? Oh, that's her screen. Okay. Yeah. And does it work now? Okay. I think it's still on Zoom. Still no voice on site. Oh, one worst case, we just put the microphone on.
Yeah, I don't get it from here. That's the issue. There.
Audio device. Yeah. Will I make your host?
Okay. Yancy?
Yes.
Here the voice device is the system.
I can sorry. I think, oh, it's go there. It's a go again, the projector. I can test again. Can you hear me?
Yes.
The speaker out to the system.
Yeah. I mean, only the speaker on the projector works.
Maybe we could just do this instead.
Let's give it a try. I can speak. Does it work?
Hello. Hello.
Yeah. So, yeah, I think we just we can do this hack. I don't know, the system doesn't work. Audio test. Audio test. Yeah, I'm testing. No, doesn't work. I'm testing. Okay. Yuanzhen, can you start? I think it works. I think it works.
Does it work?
Yeah.
Okay. Sounds good. Should I start? See, should I start?
Yuanzhen, you can start.
Okay, I'll start. Okay, thanks. Hello, I am Yuanzhen. I will talk about controllable image and video generation today. So the motivation here is to give the users more control, put them more into the driver's seats, and allow them to control for subject, style, shape, material, and composition. So I will talk about some of our explorations in these areas, but of course, some of these areas are active areas of research, and there are a lot of related works, including from many of the speakers today. So I encourage you to also check out their work. So I will cover Dream Booth, Hyper Dream Booth, which is a follow-up, and a few style customization works, and also shape and material and composition. So Dream Booth was the work that we published last year at CVPR. So the idea was that the motivation was that we don't necessarily want to generate images of any dog. We want you to be able to generate images of your dog, of a specific dog or a specific object. So for example, in this example, you give it a few Caro images on the left to specify your subject. And then you can generate images of this specific dog in various contexts and various environments with the different interactions with its environments. And here are some more examples. These are some sunglasses. Again, on the left are the few input images, and on the right you can generate images of this specific pair of sunglasses in various environments. So the idea was fairly intuitive. So we wanted to insert knowledge about these objects into the vocabulary, into the knowledge base of these text-to-image models. So we used this unique identifier, which we called V. We wanted it to be unique and rarely used, so that we don't have to first dissociate the model from what it already knows about that identifier. So we used a unique identifier, and then we also used a class word, in this case, a V dog, because we also wanted to take advantage of the knowledge that the models have learned about dogs. So we do that, and then we fine tune the model with a few of the images. Of course, in this scenario of fine tuning, because the input images are fairly few. The number of the input images is small, so we would typically also want to do some type of regularization. So this work was we had fairly enthusiastic follow-up from the community, and also there were a few contemporary works like the custom diffusion that Richard covered, and also textual inversion. But of course, Dream Booth, as it was originally proposed, it had some limitations. So one limitation is that it fine-tuned the entire model. So it involved fairly large model sizes, and also the fine-tuning was can be fairly expensive. So so there have been works that aim at making it more efficient. So for example, LoRa Dream Booth was LoRa fine-tuning is widely used in the community. And also, this year we have this follow-up work. Natanya is going to present it at CVPR, so I encourage you to check it out. It's called Hyper Dream Booth. So the motivation was that we wanted it to be feed-forward. We didn't want to do a lot of expensive fine-tuning. So we said that, okay, can you give it an image and then have a feed-forward network to predict the delta weights. So this is that's the hyper network here. So that gets you quite a bit, quite far, but not all the way there. So when we did that, we sometimes noticed that we would trade off some subject fidelity. So then we followed up with a second step of this sort of fast fine tuning. You would do a little bit of fine tuning on top of the hyper network to get you sort of all the way there. So this is sort of how the hyper network is set up. And then a second step of fast fine tuning. And in the fast fine tuning, we built it on top of LoRa, but sort of made it even more compact so that you would have a very, very small delta network, delta weights, delta model on top of the hypernetwork weights. Then you end up with something that has a very nice trade-off between speed, model size, and also subject fidelity. And then we also wanted to do this for style. And when we, so the idea is that you give it a few images or sometimes one image of a specific style, and then you want to generate more images of that style. And we really wanted the style to not just capture sort of the brush texture, but also capture sort of the essence of the style, both the form and the essence of the style. So we did this work called Style Drop, and the results were quite good. On the left is the input style image, and then on the right are the results. Here are more examples. So this work, when we did it initially, we built it on top of Muse, which I'll briefly cover, which was a masked transformer model, which was different from the typical diffusion models, but it had some nice properties. I'll quickly cover. And then we used this parameter efficient fine tuning, which is adapter weights fine tuning, and we also sort of modified the text prompts to both describe the style and the content, so that it helps the model disentangle the content from the style. So Muse is a masked transformer, and the nice thing is that it does the decoding in parallel. So at every step, you would decode multiple tokens, and then pick the high confidence ones, and then iteratively then decode more tokens. So the nice thing is that it's a very efficient way of decoding. Parallelly decode all the tokens, and it potentially gives you more an easier connection to the LLM paradigm for image generation. So then we also wanted to combine multiple subjects and multiple styles, and with an efficient, for example, LoRa fine tuning. But sometimes we found that they conflicted each other. So if you had multiple subjects and multiple style, they sometimes conflicted each other. So we did this follow-up work that would try to make them have less interference, less conflict with each other. It's like a zipper. That was like the origin of the name. You zip the LoRa's so that they fit nicely together and don't interfere. So the results were pretty good. So last year we used Dream Booth on Muse to make this app for Google I/O. It was called I/O Flip. So basically, we took some images of the Google developer mascots, and then fine-tuned the model and generated more images for this game. So these are the 4 developer mascots. And then this year at Google I/O, Style Drop was used also in combination with Google's new Imagine model, Imagine 2. So to make this project called Infinite Wonderland. So basically, Google partnered with a few artists who customized the image generation with their styles, with their artworks, and then used those to generate sort of reimaginations of the Alice in Wonderland book illustrations. I encourage you to check it out. The illustrations are quite beautiful. And we also wanted to do the subject and the style customization for videos. So we did that on top of this model that we developed called Lumiere. So it's an inflated diffusion model to have a diffusion model for text to image generation, and then you lift it up to the temporal dimension, And in doing that, we used something that's different from sort of the typical way of doing it. We did away with the temporal spatial resolution and used a 3D unit that involves downsampling not just the spatial but also the temporal axis. So that sort of allows us to generate images with less temporal aliasing. And also, the nice thing that a method like this affords is that we can sort of take the fine-tuned weights from the image model. For example, the fine-tuned subject weights, dream booth weights, and the fine-tuned style drop weights for subject and for style, and then just sort of plug it in. But it's almost plug and play with the video model, and then you can get the subject and style customizations on the video model. So these are some examples. On the left are the style reference images, and on the right are the generated videos. And we also wanted to do this for 3D. So imagine you have your dog, again, the same setup, a few Carol images of your dog. Can we generate the dog in 3D? And also, we didn't want to do it like a reconstruction problem. We wanted to sort of give it all the nice properties and the affordances of the photorealism and also the editability of these new modern generative models. So we wanted the 3D model to be editable, to be placeable in different contexts, different environments. So initially we tried sort of almost naively combining Dream Booth and Dream Fusion, but that resulted in some artifacts. It almost sort of the views almost collapsed, and you would get these sort of flat views, and also many times a dog with many heads. So we ended up devising this iterative approach. So because the hypothesis of the artifacts was that the Dream Booth sort of almost overfit the model to the few input views. So it sort of lost the ability to generate to new views. So we wanted to get to that step. So we sort of first would do a partial Dream Booth, and then do some nerf, do some Dream Fusion style nerf reconstruction. And then we would do a little more, basically use the input images to do almost an SD edit on the generated views. It's an iterative approach, so you don't collapse, you don't completely overfit to the input views. So these are some results. Again, on the left, in each group on the left are the input images, and on the right is the result. And we can put the dogs in different environments with different accessories, in different poses. So then we wanted to do the same for material. So the idea is that can you change the material for reflectance properties? So the thought was that we really wanted to combine the realism, photorealism, and the intuitive control of the modern generative models with sort of the knobs that people are familiar with in graphics rendering engines. So in this example, can I turn a knob to make an object translucent, transparent, or can I turn a knob to make it more and more metallic? So for example, these are some results. Proful is going to present this at CVPR. Again, I encourage you to check it out. We called it Alchemist. So for example, in this example, the pumpkins are turned transparent, and the statue here is also turned transparent. We also have this continuous smooth knob so that you can sort of make it more and more or less and less transparent. And this top center example, the dinosaur, is a metallic example. So on the left is the input image, on the right is sort of the dinosaur made metallic. And these are more examples. So the top left is a metallic knob, and the bottom right is a roughness roughness knob. Again, this is sort of saying that, okay, we want these knobs. We don't want the knobs to be very complicated. We wanted a few knobs that are sort of intuitive for people to understand. In this case, we chose roughness, metallic, albedo, and transparency. So a few intuitive knobs, but we want you to be able to turn it. We want you to be able to smoothly transition between the different values. So how do we do this? So we created a synthetic data set where we know how transparent we're making the object. But the interesting thing is that even though it's a synthetic data set, when we fine-tuned the diffusion model with the synthetic data set, it did generalize to real images. So that's interesting. So first we created a synthetic data set, and second we sort of injected the scalar knob value control as sort of an additional channel, and then we just basically fine-tuned the stable diffusion model. So the results are actually surprisingly good. Like in this case, if you look at the bottom right examples, again, the bananas are turned transparent, and also this little object is also the albedo is being changed. These are more examples. Some it's not always successful. Some examples are subtle, I would say, but surprisingly good. And you can also sort of, even though the synthetic data set was controlled sort of on a again in a limited scenario, it did generalize pretty well. It also can it can also handle sort of multi attribute changes. And if you generate a few of these, and you can also recover the 3D, and it's sort of it's surprisingly 3D consistent. It's not perfect, but so these are, for example, on the right is sort of the statue made metallic, and then sort of it's generated. This material editing was done on a few different views, and then a nerf was recovered. So the last work I would like to feature is called Real Fill. So the scenario we wanted to handle was that suppose you have a nice family occasion and you take many pictures, and there's one picture that you particularly like, but somehow the composition is not what you want. You would like to sort of uncrop it, but you don't want to just randomly uncrop it. You don't want to generate like an uncropping that's plausible. You want to generate an uncropping that sort of faithfully recovers the scene or the moment that you're in. So we wanted to sort of, and typically in these settings, you would take multiple photos. So we wanted to sort of use these multiple photos to sort of provide a reference to that scene. So again, we wanted to uncrop this photo. And if we use generic uncropping or outpainting, it generates very plausible images, but not necessarily the images that you want. So for example, this plushie, this toy has a certain look, and this bicycle has a certain look. So we would like sort of to recover what could have been there, like faithfully. So again, very similar to some of the previous Dream Booth style work that I showed, we wanted to sort of insert knowledge of the scene into the model, and then use that customized model that knows about the scene to do the uncropping. So we did a sort of a lower fine tuning of the imprinting model. Imprinting diffusion model on the reference images. actually on both the reference and sort of the target image that you would like to uncrop. So we customized the scene painting model, and then we used it to uncrop. Here are more results. On the left are the reference images, and on the right is the original sort of image that you would like to sort of change the composition of or uncrop. So now it's uncropped, and you can see that the crown that this little girl dancer is wearing is pretty faithful to the crown in the reference images. These are more results. Again, on the left are the scene reference images, and on the right is the input image. And now the input image is uncropped, and you can see that the elephant logo is very nicely recovered. This is another example. So this ball is recovered, and also it generalized to a different lighting from a night scene to a daytime scene. These are more results. So Lu Ming, the first author on this paper, is going to present this at SIGGRAPH this year. If you're there, check it out. So that's it. Thank you. I cannot hear anything. If there are questions, if someone can repeat the questions, that would be good. But I don't seem to be able to hear anything from the conference.
Yuanzhen, can you hear me?
Yes, yes.
Sorry. Yeah, so sorry, come here. There's some technical issue. No worries.
Hi, this is Nathan Fry from a startup. It's good to see you again. Can you hear me?
Yes.
Okay, great. I had a question. I was curious if you were kind of thinking about applying this technology that you used for applying image editing techniques to images as far as video, like video editing, if you had kind of looked down that research path at all, and what do you think will kind of come around there?
We did do some video, sort of almost like Dream Booth on video or Style Drop on video. So those we have some encouraging results. And the other few work streams we haven't tried them on video.
Anything in the time domain as far as like temporal things and camera control in video?
That is a good question. Yes, actually, with camera control using video models, I think there are we do have some work in that direction, and also there are some published works recently, quite a bit, sort of using the video generative models, but sort of give it more precise camera controls. I think we may need to try a little harder to get like really spectacular results and very precise control. But there's a lot of there's definitely work in that direction.
Awesome. Thank you so much.
Thanks.
Thank you, Yuanzhen. I think there's no more questions.
Okay, thank you.
Thank you very much.
Bye.
Can you try again?
Yes, is Zoom
Okay.
taking this time? Yes, no. Right, testing for Zoom.
I think it's good.
Awesome. Right. Yeah, sorry about that. The interesting bit will follow after this, so you don't miss much. Right, so we're in a multi-step setting where we would like to smoothly interpolate between the extreme of being able to sample in one step and the original model where we take many steps, but we're somewhat more assured of high output quality. So what this gives us is a configurable trade-off. So depending on your particular application or your intended audience, you can find a trade-off that makes sense for you, where you can decide for yourself how many steps and what quality level you're going to go for. In a sense, it gives you the best of both worlds. Furthermore, what we've also been getting as feedback is that really we would like these methods to work with stochastic samples. So previously I did some work on progressive distillation where we're trying to explicitly map the trajectory. So we have a mapping from deterministic mapping from noise to an image, which we approximate in a way that's faster. But these deterministic samplers, they don't work as well as stochastic methods for all the different applications that we have in mind. So the solution here that we explore in this paper is stochastic multi-step distillation via moment matching. And it's the first method that, at least that we've used, where we actually often see that the student beats its teacher in terms of sample quality, at least as measured by FID, but also often as judged by ourselves. I'm just going to give you a quick sneak peek of the results. So these are results on ImageNet plus conditional generation. In the blue boxes, you will see the base model, and in the red boxes, you will see an 8-step distilled model. And for both of these resolutions, we find that the distilled model achieves lower FID. And this is actually quite remarkable if you consider how tough a baseline we're comparing against here. So the base model here has two free parameters we're optimizing over to minimize FID. One is the amount of noise we're adding during sampling. So we're adding the optimal amount of noise, which is different from the thing you get analytically when you look at the math around diffusion models. And the other thing is classifier-free guidance. So this baseline here has an optimized level of classifier-free guidance that minimizes FID. Whereas for the distilled model, there's no free parameters in the sampler, and we're also not using classifier-free guidance, and still the FID is better. On text to image, we're seeing qualitatively similar results. So this is a model trained in our own data sets, and then evaluated zero-shot in Scopco. We're doing stochastic ancestral sampling without any latents. They're directly at the 512 by 512 resolution. And also there we see that the distilled model actually outperforms the base model, even when we optimize the level of guidance. So this is what the samples look like. Some more examples. I like the line with the ice skates myself. So a natural question to ask then is, how is this actually possible that a distilled model is better than its teacher? Is the teacher not supposed to be the gold standard that we're comparing against? Where does the improvement actually come from? And I have some ideas here that I will try and explain, but definitely looking forward to discuss this in more detail later. So a diffusion model predicts the scores at a lot of different noise levels. And since the score at these different noise levels is linked, adding Gaussian noise is simply doing a Gaussian convolution. In theory, if I would give you the score at any particular noise level, you could actually calculate for me the score at a different noise level, basically if you have infinite computing. Of course, in practice, what we do is we approximate the scores at each of these noise levels using a neural net that's unconstrained. So these models, they make errors when you use them. Samples will then actually be best if our sampler is set up in such a way that these errors don't compound, but rather that hopefully they will be able to cancel out to some degree. And there's some reason to believe that certain samplers are better able to leverage this than other samplers. So for example, if you use a stochastic sampler, such as ancestral sampling, instead of a deterministic sampler like DDIM, the implicit weight that you put on the predictions at each of these different noise levels is different. And so one might achieve cancellation of error more in a better way than the other methods. And this, I think, is one of the most important reasons why stochastic methods still actually often outperform deterministic samples. But in the same time, what it also implies is that ancestral sampling is not necessarily optimal. There might actually be distilled models or ways of doing distillation that are even better if they achieve this balance in a more optimal way. What it also suggests is that if you want to actually improve upon your teacher, it's not enough to simply try and take a deterministic mapping and approximate it. Because if you approximate the deterministic mapping, automatically you get something that has an upper bound of how well it can perform. It will not be better than its teacher, but rather what you want to do instead is match distributions. And if you match distributions, you have some flexibility in how you put this weighting, and you might actually improve upon your teaching. So here's what this looks like. On the left, we have deterministic samplers governed by this probability flow ODE. And we have deterministic distillation methods that try and approximate these trajectories. So this is a class of models that or methods that include progressive distillation and consistency distillation. On the right, we have stochastic samplers that use the SDE, and where during distillation we just try and approximate the distribution. So this is a class of methods that includes adversarial methods like GANs. It also includes methods that use score matching, like diffinstruct and DMD. And it also includes the moment matching distillation approach that I'll present to you today. So the starting point for the stochastic methods is ancestral sampling. It's a standard sampling loop where we start with pure noise, then we predict the outputs, and we generate the next level of noisy data. And really the key equation here is this thing in the red box, which is the analytical posterior distribution for the next level of noisy data, given the noisy data that we have now and a prediction of the clean data. So really this algorithm is at the core of distillation, and the distilled model that we'll end up with is actually, we won't make any changes to the sampling algorithm. The only thing we'll do is we'll reduce the number of sampling steps, and we'll adjust the parameters of the model in such a way that the output will improve. So in order to inspire us on how we can go about then distilling this model to get good outputs, we've looked at the method of moments. So it's not very well known in the machine learning community maybe, but it's really one of the main training methods, you could say, from statistics together with maximum likelihood. So here moments are statistics of the data, so expectations over particular functions of the data. So for example, a Gaussian is defined by its mean and its variance, its first two moments. And what you then do in the method of moments is that you train a generative model so that the expectation over this function is the same with the generated distribution as the data distribution. Now we still need to answer the question of which statistics do we actually want to match, which statistics do we care about. And I would say that for diffusion, the natural thing to match is actually the conditional expectations of the clean data given the noisy data along the trajectory. Since this is also what we optimize for when we learn our denoising models. Right, so now that we've established what we would like to match, so we've established how we would like to identify the student model, there's still the not straightforward task of doing this in practice. The statisticians, they like to stop here basically and then do the theoretical results. And unfortunately, we actually need to make it happen. Yeah, so let me walk you through how we took this and then arrived at a concrete algorithm that actually is performant. So yeah, let's first of all start with writing out these expectations in a bit more detail. So when we sample from the student model, so that's the expectation of the generator, what we really do is we start by taking a clean sample from the data distribution. We're doing forward diffusion, so we're adding noise. Then we're mapping back to the clean space by doing one step from the student model. So the student model denoises, and this is really the model that will end up adapting for our purposes. And then we do the stochastic interpolation between the starting point and the clean endpoint, where we use this analytical posterior distribution. So that's the distribution in the generator. And we're trying to match that to the training distribution, basically. The training distribution is just the same that we use for training the original diffusion model, where we take a clean data point from the data and then we add noise. And those two distributions we're trying to match. So this kind of naturally then suggests just measuring somehow these two expectations and putting some sort of mean squared error loss on them. But this is actually still very difficult to do in practice. Even if we can approximate these expectations or measure them, we have actually something that is quite ill conditioned. So the orange curve here is kind of my first attempt at minimizing this loss. And even in this particular setting, I could evaluate it. It's something that was very difficult to optimize over. But then what we actually found is that if you put a stop gradient on this ZS, so this intermediate noisy data point, you get something that's much more well-behaved. And that then turns the orange curve into the green curve, which is much easier to minimize. So analytically, what that does is we first have the expression on the bottom right here, or bottom left here, but then the stop gradient removes the grayed out part. So the gray part here is dependent on ZFS and disappears through the stop gradient, and then we have the bottom right, which we can also write as having a loss function with a stop gradient in it. So effectively, the loss that we end up with is the inner product between the one-step sample from our students, this X tilde, and the difference in these conditional expectations with the stop gradient around. Still, one more step required to actually turn this into a practical algorithm, because one of the problems that we still have is that this expectation in the generator is not actually something that's analytically practical. So we need to be able to evaluate this for any noisy data point ZS. And this is not something that we actually have available. Yeah, we have two solutions for this final issue, which means that we have two different algorithms. One does alternating optimization, where we approximate this expectation by a second auxiliary denoising model, where we train against samples from the students. And the other is a parameter space moment matching approach, where we show that by matching in a slightly different space and using two different mini batches, we can actually get around this problem. So I'll talk about the first one first, alternating optimization of the moment matching objective. What we do is we start with this auxiliary denoising model G5. It's trained against samples from the generator. So it's trained against X tilde, but it's also regularized against the teacher. And this helps with stability. And then where we previously had this conditional expectation, we now plug in the expectations under this auxiliary model. So we also still have the teacher model, the pre-trained denoising model, that is actually not updated as we do the training. But it is used as to regularize the auxiliary model, and it also gives us an expression for the second conditional expectation that we had in the original loss. So putting this together, the bottom line, we now have a nice loss that we can minimize over for training the student model. So although we took a very different route to get there, the algorithm we now have is actually very similar to something called difference struct or distribution matching distillation, which is another approach for distilling a diffusion model into a one-step sampler. So I took this from their NERSC paper, where what they do is they have a auxiliary score model. That's fine. So this is really the same thing as our auxiliary denoising model, just written in with the emphasis on the score. And it's trained against samples from the students, and in similar ways what we're doing. And actually, it turns out, yeah, even in the loss, it looks the same. Actually, it turns out that the two methods can be seen as equivalent in the one-step setting if the noise schedule is chosen in such a way that the noise point that you start with is actually purely independent of X, but also independent of the intermediate noisy data that you're sampling from, which is typically true for the first step. But this doesn't actually carry over for more than one step. So as soon as you do more than one step, this relationship actually breaks down. And the alternating optimization approach that was shown you previously can actually no longer be interpreted as moment matching, as score matching, sorry. So moment matching is no longer equal to score matching in that case. Yeah, we have a mathematical appendix in the paper that looks at this in more detail. And it's a quite interesting relationship where both approaches can eventually identify the same distribution, but actually do take a different way to get there. So what we've achieved so far, you could say, is a generalization of difference plot to the multi-step setting. But actually, if you look at the exact details, it is actually subtly different. There's still some downsides also to having this auxiliary model. So first of all, optimizing an auxiliary model in a generator in an alternating fashion is kind of like training a GAN, and it also has all the issues that we associate with GANs. So it can be unstable. There's no simple loss function that we can monitor for convergence. And even if you are convergent, it's actually not entirely clear what the objective is that we optimize. So all the analysis we've done so far kind of assumes that this auxiliary model actually is able to fully converge to this conditional expectation that we really wanted to capture. But of course, if that doesn't happen in practice, and of course it doesn't, we really have this dynamical system that might do something different than what you think it is doing. So the question is, can we do without the auxiliary nosing model? It turns out we can in an approach we call parameter space moment matching. So here we start out with the auxiliary model that I showed you previously, but we try and make it instantaneous. So we try and remove its dependency on the state. And we do that by, at any time when we call this auxiliary model, we now initialize it fresh from the teacher. Then we do one single atom optimization step with one single mini batch, where we have here a learning rate and a preconditioner. And now what we'll do, we'll take the limit of this learning rate to 0 and plug in the result in our loss function for training the student model. So this looks as follows. I'll just point out some of the terms. So L5 here is the loss for the students, which is the same as the alternating case that we had previously. But now by taking the limit with this learning rate to 0 and doing one atom step, we actually remove the dependency on this phi model. And what we'll now have instead is this this term, which is the Jacobian of the prediction of the teacher model. We'll have this lambda term, which is the preconditioner used in Adam. So that's a choice. We could also use SAD, and this term wouldn't be there. But yeah, of course, in practice, Adam also always beats SAD somehow in deep learning, and also in this case. And then this gradient term is the gradient of the teacher loss, basically, on our generated sample. So putting this together, we have something that no longer has the auxiliary model in it, and that we can easily optimize over for training the student model. Turns out, again, look at the mathematical appendix to see the details. Turns out that this is the same as doing moment matching in parameter space, where the thing that we're now minimizing is the norm of the expected loss gradients of the teacher model on generated data. So we're saying we're successful if the teacher has a small expected gradient norm when evaluated on generated data. Another way of saying the same thing, what we're trying to achieve is that we're trying to set the expectation of this gradients equal under both the generated distribution and the data distribution. But of course, since the teacher has actually been trained on the data distribution, we'd expect its gradient to be 0, near 0, when we evaluate on the same distribution. Otherwise, it's the same thing as saying it hasn't yet converged. So if it has converged, the gray part here is actually 0, and we can leave it out from the loss. So putting this together into a practical algorithm, we have the following. At every iteration, what we do is we sample 2 independent mini batches from the data. We use both to sample independent next step samples using the distilled generator. Then we take one of the samples and evaluate it using the teacher, where we evaluate the teacher loss and take the gradients and do the preconditioning using Adam. Then on the other batch, we have this loss function where we plug in the results from the first batch. And this is actually then the loss that we minimize over when learning the students. Yeah, so it seems quite convoluted maybe, kind of black magic how we get here. But actually it is very closely related to a method that's very well studied in the statistical literature, especially also it's quite popular in econometrics. And this is called the efficient method of moments. It's already a somewhat older method, and it works as follows. So what this does is it first estimates a teacher model using maximum likelihood. Of course, in our case, we train a diffusion model with a denoising loss that doesn't quite correspond to likelihood, but it's at least approximately the same. Then in their case, the moments are given by the score of the teacher model, so the gradient of the log likelihood with respect to the teacher parameters. In our case, of course, we use the gradients of the denoising loss. Then they train a student model to match the expected gradients under the student model and under the data distribution, which in this case should both be 0. So what this really means is that if successful, they've trained a student model such that the teacher distribution, so that the teacher basically cannot see the difference between generated data and real data. So when you evaluate the gradients of the log likelihood with respect to the parameters of the teacher, well, the results on both the generated data and the real data is the same, so the teacher cannot see the difference. What they then show is that under some assumptions, this is actually statistically efficient. So the student model attains the same statistical efficiency as the teacher model that is trained using maximum likelihood. And this is why this is called the efficient method of moments. Yeah, more practically speaking, what it gives us that we didn't have in these other methods is that we have this well-defined loss function that we can actually monitor during training. So we have a loss that hopefully goes down as we optimize. And if it doesn't, we need to do something about our optimizer. And this is not something that we have with GANs or with consistency distillation methods or Diffenstruct or other similar methods. And this has been very useful for us when developing this class of methods. So both of these approaches for moment matching, the alternating approach and the instantaneous approach, both can be used with and without classifier-free guidance. In practice, what we see often is that as you increase guidance levels, we get higher inception score and higher clip scores, but FID gets somewhat worse. Which is similar to what we see with when we apply classifier-free guidance to the teacher learning. Yeah, the fact that you can actually do this is not entirely straightforward. So yeah, if we have the time, I'll briefly explain how this works exactly. Yeah, okay, good. So basically what we do is that in the algorithms I showed you previously, wherever we have an expectation of the clean data generated by the teacher model, we'll actually swap it out for a guided prediction. So this is a prediction depending on a parameter W that gives us the level of classifier-free guidance. And so that means that even when we evaluate the teacher loss gradients, we do so with respect to this guided prediction. Which means in practice that you also need to backpropagate through something where you might do clipping on the prediction or other discontinuous things. In practice, what we do in that case is we just read it straight through gradient estimates, and that works just fine. So also the reason that this can actually work is that so far we've assumed that the expectation with respect to the data of the teacher loss gradient is 0. If this is not true, we'll actually end up learning a different distribution in our students than the data distribution, which in the case of guidance is also often actually what we want. So when you use a lot of guidance in your diffusion sampler, you're asking for something that is not necessarily representative of the data you train on, but that is somewhat more aligned with your text description or somewhat more typical. And often these are the kind of samples that we actually want, that we become more persuasive. So when we apply these methods with guidance, what we're saying is that we want to match the distribution for which the loss gradient would be 0 if we evaluate with respect to these guided predictions, if such a distribution exists, which might actually not be clear in general. In practice, what we get is we get samples that look very similar to the samples we get from guiding the teacher model, but the effect is actually even stronger. So in a sense, this distillation method exaggerates the effect of guidance a little bit, which you need to keep in mind when you set the guidance level. So I want to revisit the results again, but now focus on the differences that we see between the alternating and instantaneous approach of moment matching. So in the green boxes, you will see the instantaneous approach, and in the red boxes, you see the results for the alternating approach. And what we see in general is that the results for the alternating approach are a little bit better, FID is a little bit lower, but the results are quite small, at least when taking enough sampling steps, and both are still better than the base model. If you take fewer steps, then sometimes the difference becomes larger. If you take too few steps, the instantaneous approach starts breaking down somewhat, but it actually fails in a quite graceful method, quite graceful way, where what you start to lose first is sample diversity, which makes FID go up, but the sample quality actually remains very high, and inception score might actually even improve as you go into fewer steps. Also in text to image, we see qualitatively very similar results. So again, the alternating approach does slightly better than the instantaneous approach. Both do better than the base model when not using any guidance. But when using optimized guidance levels, only the alternating approach does better in this case. Although even the instantaneous approach here does beat basically all the other distillation methods that we compare against. Right, so that brings me to the end of the talk. What I would like you to take away from it is that we believe that diffusion models really need to be fast in order to be useful and in order to be interactive. And for us, multi-step distillation is really the right setting to think about this, since it gives you this configurable trade-off between quality and speed, and allows you to strike the optimum balance for your particular application or your intended audience. We also find that moment matching is a useful paradigm for doing this distillation, because it gives you support for stochastic samplers, which we think is key. It gives very strong FID results in practice. It allows you to extend these other methods like different and distribution matching distillation to the multi-step setting. And it gives you this nice non-adversarial interpretable loss that we can use to actually monitor progress, which has been very useful. Thanks. Hopefully we have time for some questions.
Maybe I have one question in the audience. You could use this one or yeah.
Other distillation methods like the one using discriminator. Do you think that returning to the pipeline using Ghana is not the correct looking better results?
I think GANs can also be made to work quite well. Definitely various authors have shown that, like the stable diffusion authors that you mentioned. At the same time, I feel like GANs are always a pain to get to work done. Like it does require this top level of practitioner to actually get them to work. So that's one area where I hope that these other classes of methods will prove a little bit more robust and easier to use. And then with GANs, even though the samples look great, sometimes there's still hidden issues like reduced sample diversity, which you actually have a lot less of with this approach. So in the paper, we have some more content on, for example, ImageNet, where if you plot like 100 samples for one particular dog breed, it's very easy to see whether you actually retain the sample diversity that you started with. And with this class of models, we do. But at least from what we've seen with many adversarial methods, you do lose a lot more sample diversity.
One of the I see with the model, they lot from time details.
for example, then do you think that using our loss, also our loss related to the exchange, improve it? Right, so this class of methods tries to match distributions and in order to turn the pixel-based mapping. And that aspect I do think is important. So for distillation methods like consistent distillation and progressive distillation, where you're directly trying to match outcomes in pixel space, you might have a bigger risk of losing these details. Although also those methods can be made to work quite well.
Yeah, very interesting talk. So, in this, the members of this paper is you use the momentum in the different time step, right? So you try to maintain the moment in different time step, right?
Well, maintaining a moment across different time steps, I'm not exactly sure what you mean by that. So what we're trying to do is we're matching the conditional expectations of the clean data given noisy data along this directory. What we're trying to match is the expectation under the student model and under the data distribution, which is not the same as maintaining it across the sampling process.
Okay, so like in the they have video diffusion model, right? Like they have a temporal axis. So do you think we can use this similar technique, but take like a 3 second teacher model, but get like a student model that can generate 5 second video? Is that possible?
So the question is whether we can use this in the video model using the dynamics of the video.
Yeah.
I think that would be very interesting. I don't see it immediately, but yeah, we could think about that more.
Let's thank Tim again for this insightful talk. Thank you so much. So next we have Tian He. She'll present our competition results. For participant presenters, if you meet on the right side.
Thank you for everyone for attending our workshop and participate in our challenge. I'm here to share the challenge results. Before we dive into the results, I'd like to briefly talk about how we measure the model performance and what's in the benchmarks. So on the T2I benchmarks, we created a prompt sets with 4,000 prompts combining existing academic benchmarks and also some prompts that we generated through our Llama 3 model. So for the academic benchmarks, we randomly sampled prompts from T2I Kanban, prompts, breakbench, and flow bench. The sample size is proportional to the original benchmark size. And for the generated prompts, we leverage our benchgen system that can produce media generating prompts with diversity in content, the sentence structure, and complexity. So in benchgen, we first sample a graph structure to represent a prompt, where a string represents major visual entities, and a node is representing an object and or an attribute, and the edge representing the relationship between them. And then we specify the content category of these major visual entities and ask LLM to populate the trees and combining every visual element into final prompts. This one cloud below demonstrates the 250 categories that we've used for building this magic prompt set. And specifically, we have about 550 prompts that contain visual text, given the recent interest in this space. And on the evaluation side, we've been using human evaluation as the final criteria to measure model quality. And we have two evaluation tasks, one for visual quality, that is whether the generated image looks good. And the other one is for the instruct following, that is whether the generated image match the prompt. And here are the illustrations of the evaluation UI for those tasks. For the visual quality tasks, we ask raters to rate the image on a scale of 1 to 5. And for each scale, we provide general descriptions and extensive examples in the guideline to calibrate across raters, as evaluating visual quality can be a bit subjective. And for the instruct following task, we adopted the vision question answering style of evaluation, where we generate an atomic question regarding each visual element in the prompt and ask readers to give a yes or no answer. And these questions are generated using LLM, but we also went through human reviews to ensure they are accurate. And we found this type of evaluation are very consistent, especially for long and complicated prompts. So for both tasks, we also use auto review to further ensure robust results. And here finally here are the leaderboard for the text to image track. We show the overall performance as well as the breakdown performance along the instruct following and visual quality dimensions. The overall performance is measured by the percentage prompts that has passed the certain threshold for both axes. And also considering its unique challenge, we also specify the visual text generation performance in this chart. And based on the evaluation results, let's congratulate Team Taskbeer, Team Lumia, and Team Spring Diffusion to be the top 3 winners for this track. And especially congrats Team Taskbeer for achieving the best performance of visual quality. And for reference, we also included the 2 well-known commercial models, Dali Gray and Stable Diffusion Spray evaluation results on the right. And we can see that there is still a gap between the top dynamic models and top commercial models, especially along the instruct following and visual text generation dimensions. So we'll discuss more on this in the panel discussion afterwards. And next, let's switch gear to the image guided text editing track. So for this benchmark, we collected around 1,000 images covering a diverse range of content, and for each image, we asked annotators to write editing prompts that are compatible with the image. In general, there are 5 types of tasks, and the word cloud here visualizes the more detailed structure of editing for each image. And similarly, we also use the human evaluation, and we show the raters the instruction prompt, the original image, and the generated image. And since the final visual quality is also depending on the original image, we only evaluated along the instruct following dimension. So for that, we will ask 2 questions, one regarding the editing fidelity and the other regarding content preservation. And similarly, we adopted the multi-review schema to ensure the consistency of the evaluation result. And with this approach, here is the final results for the eye-to-eye track. And we have Team Shunju and Hao Edits plus and Team Taskbeer again as the top 3 winners for the eye-to-eye track. Congratulations, everyone. So with this, I will pass it to the participants to talk about their work. Thank you.
Are you online?
Hello, can you hear me?
Yes.
Okay, I'll share my screen. Okay, so hello everyone, my name is Zhu Xuan, and I'm really happy to have this opportunity to present our solutions in the CVPR 2024 GenAI Media Generation Challenge Workshop. This solution is for task-guided image generation, and we have provided our solutions and documents in this link. You can scan the QR code for this solution. As has introduced above, the instruction-guided image editing will provide an editing prompt and an editing image. And following the editing prompt, we will edit the image to the edited image. And there are some previous solutions. The first step is the diffusion model fine-tuning, which is represented by the instruct pix-to-pix. In this line of work, they will fine-tune the diffusion model by providing data pair and the instruction generated maybe by some language models. And the second line of work will be large language model and diffusion model added fine-tuning. By combining these two models, the work smart edit and some following works fine-tune the LLM and diffusion model correspondingly based on data pair. However, these two types of methods all cannot fully use the language understanding ability of LLMs, because in the first part of solutions, they will only use the language models for the data generation and do not use the data understandability in the diffusion model fine-tuning. And in the second line of work, the large language model is fine-tuned and the feature cannot be fully understood by the diffusion model. So instead of doing in this two line of work, we directly use two based methods by combining the diffusion models with the large language models. So here's a pipeline of our solution. It contains 4 steps. The first step will divide the edit type based on the editing prompt. And the third step will determine the edit object and the edit mask based on the GPT-4 and the grounding sum. And finally, we will use implementing model and if edit, which is a global image editing method to edit the image. So we show the pipeline step by step. Firstly, we will determine the edit type. Here we'll provide one editing prompt for each category. For example, if we want the first image to make the horse into a unicorn, it is a local edit because it only edits a local part of the image. And for the second one, the background edit have her work on water. We'll change the background from the land field to the water, so it will be background editing. And for the third one, more furniture. This will be a global edit because it will change the whole style of the picture. And the fourth one have him be holding a surfboard. It's an addition editing because it will add a surfboard into the image. And finally is the remove, which will remove the mask from the image. We separated these 5 categories because they will use different editing types in this solution. And all the given image in the benchmark will be categorized into these 5 editing types based on GPT-4's performance. And after that is the step 2 and 3. It will provide us edit object and the mask. For example, the first one, make the horse into a unicorn, we will get the edit object horse. This will also be generated by GPT-4o. And the second one to the fourth one will have edit object none because they do have an edit object, but we'll edit the whole picture or add something into the picture. And the final one, the remove, we have an added object as the remove object. And for the mask generation, we use the grounded SAM to get any words mask using the ability of the grounded channel. And finally, we use brush light to do inpainting by, for example, the first image we will change the horse, the mask region of the horse to the unicorn that directly generate a unicorn into this region. And for some images such as changing the horse into white or changing color or any texture of the image, we'll use width of the corresponding image. And for the second and the fourth and the fifth image, we will all use brush light to do inpaint and get the final result. And for the third one, because it is a global edit, we will use inf edit, which is a text-based image editing method by giving a target text prompt. Finally, we show some comparison results of our result and previous instruction-based editing methods. The first code showed the original image, and on the top is the editing prompt. And the second one is the method which comes from the first line of work, which fine-tune diffusion. And the third code comes from the line of work that fine-tune language model and diffusion model correspondingly. And this is end of my presentation. Thanks, everyone.
Let's thank you for the presentation and for her, I think, a participation in the workshop and the session. We're going to award her with Quest 3 and a story, Ray-Ban Stories. We'll have to make a award for her. Thank you, Ken. Next up, we have Manuel.
Right. Yeah. Hi, I'm Manuel, and this is basically our submission. I'm going to try to be brief, so I'll just give you the very quick TLDR of what Lattice is. The idea is that the method that we use here is zero-shot image editing, so you can just basically plug this into any existing text-to-image model with no optimization or fine-tuning needed, no external components or other more complicated pipelines, and you get a model that can do image editing. We designed this model to be very versatile, or this approach, so we can edit multiple concepts at once. The method also does implicit masking. So by itself, it computes basically a region of the image that's important for each edit and restricts the editing to that region in the image. And as you can see here, here's some examples. You can basically do local edits, replace objects, add things, do more abstract edits by changing people, remove things, change the overall style, and so on and so forth. And what that looks like applied to the magic benchmark, the magic challenge. Here are some examples. So in general, you can see that, first of all, the images basically stay very, very similar. We only change the thing we actually want to target in each image. And it applies to different styles, different types of edits. Before concluding, I would like to share some insights on this as well, because this is an existing work that we were presenting as well at CVPR. If you have any further questions, but maybe some specific insights about the challenge itself. So first of all, like constructing a challenge is hard. This is an experience we had ourselves. If you're constructing benchmarks for image editing, this is far from a trivial task, and especially if you do this syntactically, to some extent, there might be some interesting artifacts. So some things we have observed, for example, the prompt, have the sunset be a sunrise, obviously doesn't really change anything in the image because you're replacing one thing with another that's visually somewhat indistinguishable. Another interesting example is when maybe the generated image that you started out from didn't adhere to the prompt very nicely. So transform the moths into butterflies. It's of course plural, but there's only one moth in the image. But if we then plug this into ledits and basically remove the moth and add butterflies plural, we get multiple ones. Whereas if we did change the prompt here to what was probably intended with this edit, having one moth and turning that one into a butterfly, then we get more of the expected output. And I don't want to just dunk on the challenge creators here. I'm going to be a bit self-deprecating as well. There's one specific set of tasks that we observe ledits to be very bad at. While the examples we showed previously basically underpin that ledits is very good for a lot of different things, it is, after all, very object-centric. So there were, I think, about 30%, probably, maybe 25% of all of the edits in the benchmark just replace the background. And as you can see here, that doesn't work very well with ledits. As I said, very object-centric. So you have the object in the image, and if we then here from left to right just increase the strength of the hyperparameters, we end up replacing the original subject instead of changing the background. So that is sort of a very confounding factor for the benchmark results we've seen earlier. Quick shout out to, I think, almost all of the co-authors of ledits. They're actually in this room, apart from Christian. And then other than that, ledits is a paper here at CVPR. So if you want to learn more or chat to us and ask any follow-up questions, please feel free to come by our poster session on Thursday in the afternoon. And also all of our, there's a demo and the paper on our project page. Ledits as a pipeline is actually also integrated in the diffusers library. So if you want to try it out, feel free to use it. Thanks.
Thanks, Manuel, for his participation on this challenge. For his precision award, we'll give him quest 3. Thanks.
This presentation.
But I think the website is in Thursday.
Okay. Okay, we're good. No, I think that's if you don't use it.
Okay. Hello everyone. Today I'm going to introduce our work, Lumina, which is a multimodal generation family, and with flow-based attribution transformers. And this is also our solution for this competition. And actually, there are two related papers, which is the first one is Lumina T2X, which is a unified framework for multimodality generation with flow-based attribution transformers. And the next one is Luminanetics, which is for making Lumina T2X stronger and faster with NextDIT. And the core components of our Lumina T2X framework is FlagDIT, which is a flow-based large diffusion transformer. Compared to the original DIT architecture, here we introduce some new architectures like rotary precision embedding and RMS norm, QP norm, so on. And as shown in our list code, our model is compatible with mixed precision training and flash attention with enable is for good training efficiency. And which also support is with a very large parameter space up to 7 billion and also supports process of long sequence like more than 100,000. And to unify multimodality, we encode different input signals into 1D sequence. And here we use a learnable next line and the next frame token to model 2D and 3D input signals. And here's some results of here's some generation result of illuminated text like images, videos, and multi-views. And in addition to the model architecture, we also introduce, we also introduce some advanced inference techniques to achieve some zero-shot downstream applications. For example, as we use different transformer with 1D sequence, we can our model is compatible with the context length extrapolation techniques used for large language models to achieve resolution extrapolation. So our model can generate image with resolution up to 2000, and the model is only trained on 1K images. And with some attention manipulation, we can also achieve zero-shot style consistency generation and compositional generation. And here's some results. And also with a simple noise injection, we can achieve high resolution editing, and the result is also quite impressive. And after that, we also introduced LuminNext with NextDIT, which is an improved version of FlagDIT. And here we introduce some architecture modification like 3D row superposition embedding and sandwich normalization. And we also propose some newly proposed some inference techniques like time-aware scaled rope to achieve better resolution extrapolation and and we also propose sigmoid time schedule and time-aware context job for few-step inference. And in addition to this, we also plan supervised fine-tuning on high-quality images can achieve a significant performance boosting on our model to generate photorealistic images. And here is a comparison of our three version Lumina-T2X, LuminNext, and LuminNext with supervised fine-tuning. And the middle version is we use for the computation, but if you are interested with our best performance, please try our demo. And for more information and details, please refer to our open source code and paper. Yeah, that's all.
Thanks, Roy, for his presentation, for his participation and I think positioning of his result for learning with his question device. Thank you. Lastly, we have Akio and Chenfeng presenting their work on stream diffusion. Yep, we're good to go.
Oh, so hello everyone. My name is Akira Kodaira, and my name is Chenfeng Xu. We are both PhD candidates at UC Berkeley. So actually today our topic is a little bit diverged from the image generation and edit quality capability, but we focus on more the image generation efficiency for real-time application. Today we're going to talk about our work in stream diffusion, a pipeline-level solutions for real-time interactive generation. So diffusion model unlocked the paradigm of the high fidelity image generation. However, most current use case is based on the request and wait format. Like also the popular backbone, like the diffuser from Hugging Face, is also optimized for this kind of use case. However, there's also
Okay. Yeah.
Yeah.
Let's try this one.
Oops.
Sorry. It's an issue. Just turn off.
I turned off.
Bring that.
Okay. So however, there's also included the amount of interactive use case. So what is interactive use case? So for example, game rendering is one of the interactive use case example. So right side is the input image, relatively low texture and a low polygon. By using diffusion model, essentially we can do the high resolution and the realistic text generation and even style transfer in the real time. So this kind of use case, user observe the game screen and make action to generate a sequence of input images, and this diffusion model do the image edit for those sequence of image and do this kind of iteration loop. However, currently there's two main big challenge make this application less practical. One is poor efficiency, and second is time inconsistency. To address these two problems, we developed a stream diffusion, which is a pipeline optimized for real-time interactive generation application. So these two are the example using stream diffusion. They are all playing in real time. You can join this image in this speed. Well, that's awesome. Okay, so stream diffusion contains several important modules in the algorithm side, and also engineering effort side. Due to the time constraint, today we are going to explain the most important module called stream batch. As you can see on the left side of the image. So in the usual conventional pipeline, once the pipeline accepts the input, pipeline needs to do the sequential denoising step to the end, then returns some output, then can finally accept a new input from user. So while doing this denoising sequential, user cannot put into new action in input into the pipeline, and this makes the interactive less smooth. On the other hand, our stream diffusion uses stream batch. So once we accept the input, we put the input into stream batch and just do the denoising one time. And this stream batch denoising will denoise for all the different denoising level latent the same one once. Then get some one output. So essentially, the workflow is the one input, one denoising, and you get one output immediately. Well, so since this is challenge, so we use the stream diffusion to do the challenge. And here's the result. Since our method for image edit side, we just based on the pure SD edit base. So you can see that the generation code edit code is not good. So this is prompt. So you can see it's like change everything, and this is not pure dragging. But our strength is more in the inference side, speed and efficiency. So the top left is the real-time face swapping controlled by text prompt. We can put a new text in real time and change the face as you want. And this is some stride transfer application. This is real-time AI-assisted drawing. You can draw stroke, simple stroke, and AI diffusion model turn into the high-fidelity image. And this is interactive content creation in real time. So probably you might think this stream batch is just an engineering trick, but however, it actually has very strong ability for context and time series application.
Yeah, next I will talk about how our stream batch can also improve the time consistency. So you can see that here we have a sequence of inputs, and even we use original stream batch, each output is still generated independently. This means that the context is not fully used during the generation. And our stream batch has a natural advantage. That is, we can directly leverage the future frame into the generating and the previous frames. As you can see here, we use a very simple trick that is using the future frame attention. you can see when the sequential inputs comes in, we can leverage the future frames to attend to the frame current journey. And you can see that this means we can leverage the temporal context to help the temporal consistency. And here's the results. So you can see the most left image is the input, and the medium is the baseline. Baseline is simply the edit. And with our future frame attention, the time consistency is significantly improved. You can see the middle part has lots of noise clipping, but for our stream batch, we can have better time consistency. And today we are also excited to share that we checked the GitHub, and we are very excited that our stream batch has got lots of attention and people like to use it. We get the 9,000 stars, and we really appreciate that users can use it to do some very creative applications. You can check these applications in the Twitter with the tag of the stream diffusion. And here are some I think representative applications. The left part is the sound visualization, and the middle part is the AR/VR application.
Maybe. On the right side is the user using the as a projector on the left side. So we're really delighted to see users making such a creative content using our screen platform. Yeah. So that's all our presentation. So thank you so much for listening.
For his participation in both the ITI and T2I challenge, for giving them the Ray-Ban and Meta smart glasses.
Thank you. Thank you so much.
Thank you. Thank you.
Yeah, maybe next program.
So I think next up we have our panel discussion. And our panelists come forward to take the table here. Yep. So here, please take a seat. Sure. We'll just use this seat. And then we have our host, Kevin Jiao Ma, to host the panel discussion.
Yeah, I think it should work. Oh.
Let me just switch to, I think,
this slide.
Yes. Okay, yeah, sorry.
Yeah. Anyways.
Yeah. So.
Okay. Hello, everybody. I'm Kevin. I'm a research scientist in Meta AI working on image and video generation. Really excited about this opportunity to be able to host and moderate this panel discussion. We just have about 30 minutes together, and the goal of this panel discussion to get the latest juice from an expert in media generation. And today with me, we have three world-class, well-known researchers and professors with us. Next to me, we have Richard. Richard Zhang, he was a PhD student from UC Berkeley. He is now a researcher in Adobe. He was recognized as an innovator under 35 by MIT Tech Review in 2023. And next to him, Richard is Ishan. Ishan is a researcher from Meta GenAI, who is now leading the video generation efforts. He was also featured in MIT Tech Review 35 Innovator under 35. What a coincidence, huh? He was also in a famous Lex Friedman podcast that talks about self-supervised learning. I encourage you guys to check it out. Lastly, we have Jin. He was a postdoc at MIT, and now he was also a research scientist from Adobe, and now an assistant professor at CNU, focusing on a generative model for content creation. A fun fact that I've learned about Jin is that he actually maintained a web page called Cat Paper Collection, which basically collects all sorts of research papers that have their experimental results that have cats. So that was a really fun hobby that I learned about him. Let's get a round of applause for our panelists. So let's begin our panel discussion. So we have seen a lot of evidences today, where over the years we have seen like image and video generation. We can find crappy image generated, good image generating, stunning image generated, and even created image generated or video generated nowadays. And a lot of people are using them for their daily life, for their work, for their improving their work efficiency. And so the first question that I have for the discussion is, where do we, as as an expert in this field, where do you see this generated models will advance in the next 3 or 5 years? Right, we have seen even just the past few weeks, there were so many amazing like video generation models that came out as well. So how do we see them being changed in the horizon of, let's say, 3 years or 5 years? I don't know if anyone will be interested to take on the first questions. Yeah, that's what
I think at least one thing I think will happen that we should probably see in a few years already happen is the generative models will become the models, the video and image prediction models are likely going to be the models that also learn the best representation for solving tasks, especially in video for temporal. I think one of the biggest challenges in video understanding was basically that for decades together, when people come out with a video understanding data set, then you basically improve the image representation, and then that image representation will do the best job at that particular video understanding task. And so you would solve basically every year, there would be a new data set. The next year, the best image representation would basically be the thing that would be necessary. I think for me, really the main thing is that video generation probably is very different from like video classification, where you actually do need to have some understanding of motion, understanding of temporal coherence, consistency, all of that. I think that is why probably in the next few years, we actually are going to see these models be the ones that develop very consistent video understanding as well.
Okay, maybe I'll build a bit on that. On top of generative models becoming more powerful, right now we're seeing that before there are image generative models, now there's video generative models coming every day. What we're seeing a clear trend of, this is not even a 3 to 5 year thing, it's more a 1 to 2 year thing, is that everything's going to be multimodal. And there's kind of good reason for that, because if you have to learn something about images, something about video, something about audio, something about language, in the end, it's kind of more efficient to represent the kind of underlying world processes that kind of gave rise to that data. And that's perhaps why the generative models are also becoming stronger and stronger representations for discriminative tasks as well. So basically everything is just starting to unify, and then at some point we'll run out of data. We'll be training on every single type of data of every single type of modality, and then from there we'll see what's next.
very interesting.
Yeah, I think it's harder to predict the future. I guess I can predict it might be harder to follow the archive papers in 3 to 5 years. So very hard now. I think I like playing computer games, so I hope the generative models can change how we create games, and will see our AI environment is requires us to connect generative model with all these neural rendering techniques to create reusable assets for the gaming and the AI. Thanks.
Sounds good. Yeah, so actually go on top of what Janine was saying about what the generative models that can do in the future. The next question that I have is like, given all this advance of like media generation, regardless it's like image, video, or even 3D, and we have seen like language model like being really used in our daily life, and how do we see media generation models being changing our human lives, and where do you see the potential of biggest changes that could be coming? Not sure who will be interesting to like. Okay, sure, here you go.
Okay, so I mean, apart from content creation, I think content creation is probably the most obvious application right now. I think probably it's also going to come down to, I would really like this, I don't know if somebody will make it, hopefully somebody does, is that when you want to, I think today if you want to, something breaks, I don't know, your refrigerator breaks or your washing machine breaks and you want to repair it, you go to YouTube, you try to find out, okay, LG model SK300, whatever 9129, how to fix the door. I really hope that basically we get to a point where right now ChatGPT, if I ask it like, hey, I want to do this, or I ask any LLM, it'll give me a bunch of steps, but it's not really grounded into what I really want there. I hope that we're basically able to get to a point where media generation models are so seamless that if I basically ask it a question that click a picture, or I have the Ray-Ban glasses, whatever, ask it that, well, how do I particularly like fix this? That's able to walk me and generate all the video of how I'm supposed to go and fix it for that particular location where I am, or if I'm stuck at a particular thing that I can't find the screw, or I don't know which particular board to move, or so on, it actually helps me do that. I hope that finesse. So for me, that is really, apart from content creation, that is really the thing that sort of melts together the understanding piece of it, because it really needs to understand what I'm trying to solve and what the object in front of me is, and then sort of is really generating to a fidelity where actually can reason about different types of bolts and like how they need to move, or like moving on like other applications of this sort.
Yeah, I think this maybe somewhat echoes to what Richard was saying about like a combination of understanding, generative, and also like a different modality, right? Do you want to extend on it?
No, that makes a lot of sense. I mean, I think for me, the threshold of when things start working is when like I start hearing about it from my mom. So so when ChatGPT came out, my mom just started sending me things that she was doing with it. Like she was using it to kind of fix up her English and things like that. So that's when I realized, oh, this is like very mainstream. Like she's telling me about this. And definitely I foresee what Ishan is saying is going to happen. I mean, right now when I'm planning vacations, when I'm trying to fix stuff or figure out how to do some gardening thing or some house the task, I'm looking at ChatGPT or Perplexity, or yeah, it'd be great if I could just get a how-to and personalized, instruction. Or if I could take a picture of whatever's broken in my house and get it fixed. So I'm definitely looking forward to that.
I feel it may change the education. I think it will be very easy to build virtual avatar. There are already lots of startups around it to create like educational like lecture videos. So everyone can even get a customized avatar to their preference. So we will have very high quality educational video, although I'm not sure it's a good thing for tenure track faculty, but anyway, so I think it will happen to reduce the cost of education, increase the benefits of this kind of massive online course.
Well, it'll free you to do research. Right?
depends on university policy. Okay. Anyway,
Yeah, that's good. So the next question that I have is, I think we will spend a little bit more time on discussing. So the question is, many of the things that we saw, like in image or video generation models nowadays, came from scaling, regardless it's model scaling or data scaling, and a lot of them doesn't come lightly, right? You need a lot of resources and compute to make that happen. But we also see that in the industry, even some of the industrial group is struggling with getting the necessary compute and scale for their work. But then in academic, that would be also prevent the software challenge. And so I wanted to actually use this opportunity for us to maybe think about first, is scaling important? If it is, there could be a gap between like industrial and academic. And how do we bridge that gap? How do we embrace the differences? And how does the study from academic could be applied to industrial scale? So I think this is something that we want to spend a little bit of time.
Yeah, these are, I think, important questions. So maybe I'll speak from a company that, I mean, it's in industry, but doesn't quite have some of the same resources as some other companies. So right now we're also struggling with some of these questions because some of our projects are kind of more modular and smaller compute. And it's difficult because not every intern project that we have can possibly be training on the whole internet. So we've still been able to find I think smaller scale, interesting scientific problems. And I think there's always going to be a place for that. And what's been, okay, so on the image generation side, what's been a great boost for our research is when Stable Diffusion came out, right? Because in the first summer, all the models, DALL-E and Imagine and Party, everything was closed. So we were trying to do diffusion model research, but using really old models. But when Stable Diffusion came out, right, it really boosted a lot of our research projects a lot. So I think open source still remains extremely important. Unfortunately, things are becoming more and more closed. So I'm still trying to be a big proponent of having big open source models. That's really important for, I guess, academics and us poor industry researchers, let's say.
Yeah, I guess we may have less resources than it's less compatible. So I do think I mean, I think there are three aspects, right? The scaling law does apply, which means if you have a model which works on ImageNet, and if your scaling law is like 1.0 correlation, you can scale up to larger data sets. We have seen that from like diffusion transformer at DIT, or even like you can first train a model on mass GIT, and then it apply to news, or even LDM, you can train LDM on ImageNet. I do think you can experiment with lots of ideas, even based on ImageNet, and oftentimes they do apply to, they can be scaled by industry labs, right? I also feel like lots of new idea was actually coming from universities. For example, if you look at like diffusion or GANs or flow-based model, like score matching, like NERV, Gaussian splatting, most of them are coming from university, although sometimes in collaboration with industry labs. So I feel like you can come up with a new idea, you just don't have, you can let other people to scale this. That's fine. And actually the situation is very similar to like computer graphics 25 years ago, right? So people can really make a movie. Why do you even need a computer graphics lab in a university? Why do you need to work on geometry? But I think this year we are still hiring for graphics faculty, so maybe we are still doing computer graphics, although it's not as popular as AI, but CGRAPH is not shrinking. The same story here, right? If you are in a university doing computer graphics, you are not supposed to compete with Pixar on making the fanciest movies and try to sell it, right? So, but you can write some new geometric algorithms that might be useful and pick up by Pixar engineers. But I think we can have different roles, and we are doing being fun with the current roles we have.
Right.
Yeah, so I think my perspective on this is very similar to like when I remember I was maybe a few years ago when AlexNet had just come out, maybe it's like now old. But at that point, it was like, okay, academics cannot train AlexNet on ImageNet. This is like too large scale. This basically can only happen in 4 places in the world or three places in the world. And so there's absolutely, I don't know, what are PhD students supposed to do? I think it's the same thing, right? Then the progression was that, okay, there were a few people who trained at Berkeley, the original cafe like AlexNet or CafeNet models that came out, and then basically everybody was trying to fine tune them, get a grip on understanding what these models are, but really people were not pre-training on ImageNet. Now it's common, and now like when Julian's saying that, hey, we can just do ImageNet, but like, yes, 10 years ago, that was not the thing, right? I think it's going to be the same thing where right now, yes, I think most people are not able to train it from scratch because it's a very resource intensive process. Large models of today are tiny models of like 5 years from now. I think like that's basically going to be the situation anyway. So in general, that does mean that we should not stop basically working on it just because industry has the resources to train it at scale today. It does not mean that's going to be the only thing to do like 5 years from now. 5 years from now, everybody will have the resources to basically train at least some version of these models. And I think the second thing Virginia's point is with, I think a lot of the innovations, I think industry is really good at scaling things, but it's hard typically to like go back to the drawing board and rethink and basically like reinvent, like invent a thing completely from scratch, which has no evidence at all of working. So essentially pie in the sky ideas. I think that absolutely has to come from academia. That's actually where like most of the industrial ideas do come from. Even taking these large models that have been released today and understanding why they're working, it's a huge challenge. I think there's a lot of theory about these models, generative models, either continuous space or discrete space models, which we don't really understand, which I think it needs, even at a small scale, you can actually do a lot of like work to understand why these models are working or what is really making them tick. So the scale aspect is really to just like create these impressively amazing images. But I think the understanding aspect doesn't really need the scale to go with it. And yes, if you work on it now, like 5 years from now, you can actually also tackle the scale aspect because that model actually becomes reachable for everybody.
Yeah, thank you so much. I really glad that I actually asked these questions on the stage with this audience. Because this is something that has been also puzzling me a lot. I completely agree with what you guys were saying about it. So I'm gonna ask you one last questions, and then afterwards we're gonna open to like an audience question. If you wanted to ask question, you might want to think about it, and then we will have the opportunity for you to like ask questions afterwards. So the last question is like more or less casual, I think, given us talking about events recently and then the difference between industrial and academic. And we have a very small audience here. What would be the simple advice for them if they were to like, I've seen people here were somewhat working on a media generation field, and what would be the advice that you wanted to give them? If years back now you are a student or you are an engineer in a company working on this, what would you do seeing now where we are and having the ability to predict what could happen in the future? What would be the advice that you wanted to share with our audience?
Yeah, it's kind of hard to answer because things are moving so quickly. So I can maybe just give some reflections on things that work well for me. Some of the kind of works that I've done. So one thing is that because these technology is changing so fast, sometimes you can think about how to make kind of a more permanent kind of contribution. And one way of doing that is through tools. So for example, I've had some work on like training a perceptual metric, and that work was from about 5 years ago. And back then, like things were more about GANs. Now it's more about diffusion models, autoregressive models. But even as kind of technology changes, that's still kind of a building block that can be used through time. There's also, I mean, different types of tools that can be developed, like kind of coding tools, for example, or I mean, network layers is kind of one type of these things. So trying to think of kind of contributions that'll outlast, you know, the latest kind of CVPR cycle. That's something that I've tried. Some of my work has also been thinking about kind of a careful evaluation and kind of setting up evaluation protocols. That's also been something that can kind of persist, you know, from generation to generation as well. So, yeah.
I think the suggestion about evaluations are also pretty close to zero, what we were discussing in this workshop, where, you know, during this like challenging workshop, we have been thinking deeply, team members have been thinking deeply, how do we fairly evaluate these models? So, would anybody interested in sharing their thoughts and advice?
I have Richard's advice is amazing. I think my thing is a little bit more, I would say slightly different, not maybe towards like CVPR or like research. But I think one thing which I personally underestimated a lot coming in, and I slowly like painfully also realized that was really important, is garbage in, garbage out is very true. So unless you actually, a lot of PhD and a lot of research is glorifies model training and understanding that, but does not really glorify either the evaluation aspects as you also mentioned, and neither what is going into the system, which is the data aspect. I think really like my analogy is like how jewelers are very good at whatever identifying the right stone. Really picking out the right data is almost as important as actually picking out the right model class. I think that is something which took me personally a long time to appreciate. But I think that's really something that like the quicker you sort of realize it, the better it is. I think somewhere along the line, we lost that skill as well. So I think I remember that when we used to do like classification or detection on Pascal, we would see data sets, which basically had about like thousands of images. Most of us could tell, like whenever we would see an image, we're like, Pascal. Then came Coco, that had 80,000 images. That point, some of us knew some images, but not all the 80,000. And then it became very hard to figure out. ImageNet, I think by the classes, at least some of us could tell what the image was. And then we went to internet scale where basically all hell broke loose. And now at this point, we don't, I think most of us haven't looked at it, what the data is and so on. This is extremely challenging, right? Like these models are being trained on billions of images or videos and multiple like thousands, hundreds of thousands, maybe of hours of video, which if you are watching continuously for like basically 24 hours a day, you really will not get any sense for what your data is. This is a huge problem. But it is also a huge opportunity to actually learn how to like or develop some skill or develop some tools to basically make this process better. If you've learned one thing, like basically in the past, whatever decade of deep learning, it is that scale is helping. Scale is helping in both in compute and data, right? But how do you visualize that data? How do you understand that data? How do you curate that data? That part is really underappreciated. It's a skill I think worth developing.
Wait, so you're asking a casual question? I can give a casual answer.
Yeah, go ahead.
I think it'd be useful to, I think research is very hard, right? There are lots of rejections, you know, for decline something, it's up and down, and it's, I mean, if you feel lonely, you can actually adopt some pets, right? So that's my advice. So if you are far away from your family members or friends, I think any kind of cats or dogs are quite useful for mental health as well. For exercise, you can walk your dog. That's my casual answer. Maybe I provide a more serious answer. I feel it's useful to doing some work, which can help other people graduate. So if you not just help yourself graduate, you can do some work which people can use your work so that they can. It's easier for them to graduate. That work might be somehow useful. So like it can be paper, it can be idea, it can be a benchmark, it can be some code base, which are easier to use. So I always think when I'm doing my research, I always think which is my kind of target customers. What can we make other people's life easier? Yeah. For example, if you provide a code base and takes a week to install, it's not making anyone's life easier. So you cannot do that. But if you, no, anyway, that's my serious advice.
Yeah, thank you so much for the discussion. It was really interesting to see how you guys were thinking about, back then, if this is where we are now, and then what advice that we should be taken, right? And I hear about how we should think about different angles of doing in research work. How we think about like going more than one cycle of the conference, or think about how our work will be able to be equivalent and useful for others, and then also jumping outside of like training and evaluation and thinking about what we do need right now as we are scaling our training. Now we just 1 or 2 minutes maybe we'll open with one question from audience. Okay, I see a hand raised slightly faster, so please go ahead.
Thanks so much for your time. I really appreciate it. One question that I have is there's a lot of talk around regulation and ethics when it comes to generative AI. So how do we see Gen AI change as regulations are enforced? Right now, the philosophy is the trend is that we have all this data and we throw a bunch of data and then we are able to learn these patterns from it and we are able to generate meaningful content. And I know Richard gave a fantastic talk earlier on talking about attribution. So I really appreciate if you can throw some light on regulations and how that will affect behavior.
Yeah, I think Goodman was being mentioned, so maybe you want to.
Okay. So I give it a shot. All that work is also shared with Junyan, so I'm sure he'll have thoughts on that as well. I think it's definitely a kind of multi-pronged solution that's required. So some things, right, just need to be regulated. Like there's some really like very bad uses of generative AI, like making kind of deep fake porn of other people and extorting them. That clearly should just be illegal. And right, we have mechanisms for just making things illegal, prosecuting people who do bad things. For things that are kind of more murky, let's say, like right now, scraping from the internet and training on it, that's really a lot of kind of legal determinations are, my understanding is a lot of legal determinations are yet to be made. And by the time that gets figured out, I mean, who knows, maybe it's too late because you have all these images circling around, being trained on each other. That's kind of what's happening in the ecosystem right now. My feeling is, as you know, like a proper capitalist, that behave like more positive behaviors happen when you align incentives towards a good thing. So that's kind of what's informing some of the research that Junyan and I are doing. So with like the attribution work, my feeling is that if these models are generating a lot of excess value, basically there should be enough in that pie to go around to reward everyone who had a hand in that. So we can kind of create a technical link between generations and training data, then that should be hopefully a good lubricant for distributing those rewards. Now, I don't know if there's enough kind of momentum in this idea for it to happen, because right, we need to have somebody that's willing to kind of do this, but that's kind of informing some of our research here.
Maybe we're open to that second question.
Yeah, I wanted to quickly reiterate on the point of like scale and academic versus industrial research. I wholeheartedly agree with you. Like there's definitely a lot of valuable research that can happen in academia at like lower scale and more fundamental understandings that then establish basically baselines that an industry then can scale. But it feels like that currently this sentiment is probably not really shared to some extent, also in the research community, because I've heard of a lot of cases where people had papers rejected or nearly rejected because reviewers basically claimed that, yeah, you didn't apply this beyond the scale of 1B or 3B or whatever, so we don't know it's actually viable, which I disagree with, and I think it goes very much against what you've been discussing. So what's maybe your idea of how we can change the sentiment in the community and ensure that this research can thrive? Because if it's not publishable, then we have a big problem, I guess.
Yeah, so I think this entire notion of like parameter-based performance, like whatever, my 1 billion model compared to your 1 billion model, or my half billion parameter model. I think all of that probably needs to just go away, and we really need to like establish compute Pareto optimal fronts to like actually do this in a proper manner. I think at some point it becomes almost meaningless to talk about comparing models until you're controlling for basically compute, or controlling for training flops, or controlling for these things. And I think in general, basically, like when people are talking about benchmarks, we all, so, okay, let's go to a standard CVPR paper today. You would have like a table where you have like a model architecture, number of parameters, maybe training data column, if like somebody actually wanted to do that. And most of it will be NA or unknown. And then basically you have like a performance on a bunch of different benchmarks. This comparison is basically a losing race, right? At this point, you don't know what you're comparing to. You don't know what it was trained on. You don't know how much time it took to train on. All you're really reporting is number of parameters. That is almost meaningless. It may be a half a billion parameter model that was trained for 20 months, or it may be a 1 billion parameter trained for 1 day. I think until we like basically add both of these things together to actually report these things and also account for training data, it's almost a meaningless comparison. At that point, it's not even like scientific. In general, I think raising awareness of this particular problem of like not having a good controlled way of comparing things is really the only solution. Reply back to that reviewer and be like, okay, yes, but can you tell me how much compute time was spent over here and whether it's the right thing to compare on? I think the entire point of having scaling laws, the entire point of having all of this is so that people understand that, okay, there is a trade-off of training compute or like training data, both together being varied with the performance. And if you don't account for that, then I don't know what you're even comparing.
Yeah, I really like the answer from Sean. I personally also completely agree with it. Like we have to do a fair comparison, and maybe this is, if we get a chance to host another workshop about this challenge, maybe this is something that we wanted to benchmark on based on the compute regardless of the model parameters and sizes. Okay, looks like we still have one last question. So.
So I actually want to follow up Richard's opinion that we have been seeing the unification of modalities architecture, and for now for image video generation, we're still using different models. Open language models, we're using SA language. I was wondering I want to ask your opinions on like the unifications of media generation and language model. Do you think we still have to have computer models for generation and language models, or we send tasks going to unify them together? Thanks.
Like you mentioned, it's hard to predict the future, but I'll give some past experience, which is when we went from GANs to diffusion models. So diffusion models were performing better, but we actually found that GAN still had their place. So Julian and I had a paper called GigaGAN. And part of that was just saying, can we scale up GANs? And what we found is that you can, but basically for raw text image, which is a more kind of multimodal problem, diffusion models are better. And then for upsampling, a low res image to high res image, actually it's a more unimodal kind of distribution. So you can kind of just get away with the GAN, which is going to be very fast and really just snap you to that mode. So we could see a situation where different models have different strengths and they can be kind of called on in different situations. So we're already seeing kind of multimodal papers appearing on Archive trying to kind of unify these things. So we'll see. It could be that we have language models that are kind of driving kind of some reasoning task, and then when we want to render into pixel space, we do something with the diffusion model or GAN, and so these things might all kind of still coexist happily together.
Yeah, I do think most of the models are hybrid, right? Even the latest diffusion model or regressive model, they actually use a GAN-based encoder-decoder. Although they don't mention that a lot in the paper, but I mean, so it's already hybrid. So I do feel like it depends on what you want, but I feel like if you already have a text-to-image model, which can generate image based on text, but why do you have to switch to a different model? I think it really depends on what you want. I think because let's say there are lots of filters which are based on GANs, like what is Snapchat filters, whatever TikTok filters. So they already have a filter which can do the filtering stuff. So why do we have to switch to a diffusion model? It really depends on what you want. Also, I feel like diffusion model and autoregressive model are kind of similar, like just the different ways to kind of divide and conquer generations. You can consider this masking is kind of adding, it's kind of like diffusion process with a structural mask. The only difference is whether you prefer continuous token or discrete token. I think they are not too much, they are not so different, but anyway. But I understand people like to have everything in usable model, but yeah, tokenizer is not based on diffusion or regressive. Anyway.
Okay, I think we are about time. Maybe we'll get a round of applause if you think our panelists are going I will hand over percent for the closing remarks.
Can we announce this? Okay. So I think I'm between you and the break for the day. Thank you so much for coming to our workshop and participating. I hope you had a good time. I think the panel discussions were really insightful. I think if we get another opportunity, we're going to try to see if we can actually extend this a little bit. I think there's a lot of important insights we get from the panel. There's a lot of potential things I think we can try to do as a community to see how we can move forward in terms of like tracking for progress, and then finding out how we actually can understand the space of generative AI. So just a quick few things on what we're going to do for the next, I think we've been presenting bits and pieces of the media challenge results. We didn't have a lot of time to go into depth on discussing what we did actually for the evaluation, or actually going to further detail of the analysis. So we'll try to work on a technical report to provide more details on this. We'll invite the participants to also try to contribute to this, and I know Mel has also provided some valuable feedback for us, which we can actually try to iterate on. And then I think we haven't updated the leadership board, so we'll do that. And then one other thing I think we're going to open source is the annotation results. So I think we'll be releasing this to the participants. Since the images are owned by, I think, the participants, I think on our side, I think we'll ask is if we could also open source the images. I think this will be a valuable data set for human evaluation as well. And then this could be also a way for us to collect data for auto evaluations in the future. So with that, I think we'll end here. And if we have another opportunity, we'll hopefully see you next time. Thank you very much again.